Linear algebra is concerned with linear equations and their representation in vector spaces. So in vector spaces, we perform algebraic operations on vectors, and we do this using matrices, which are basically 2D rectangular arrays, and we'll look at them in more detail as we progress. So here we have a linear equation representing a line, which is written in the implicit form. So we have some function on the left that's a function of x and y is equal to some constant on the right. And these constants c1 and c2 are not both 0. So c1 is not 0 or c2 is not 0. So you may recognize this line in the explicit form if we divide through by c2 and subtract c1x from both sides. So what we get is minus c1 on c2 multiplied by x plus d on c2. So this is basically in the form of y is equal to mx plus a constant being the y-intercept. Now in 3 dimensions, our linear equation represents a plane where the constants c1, c2 and c3 are also not all 0. And we can see the plane here for a visual. And in general, where we have an arbitrary number of dimensions, we also have these constants not all being 0. And this linear equation is called homogeneous when d is equal to 0 on the right hand side. So numerical examples of linear equations may be x plus 3y is equal to 1, or in 3D 2x plus y plus 1/2 by z is equal to 0. And examples of nonlinear equations are x plus root y is equal to 1. So here we have a radical, and x squared plus y is equal to 2, where x squared is a parabolic term. Now let's extend our ideas from linear equations to systems of linear equations. So here we have p equations with q unknowns that we want to solve for. So we write this general form with the coefficients of the variables from x1 to xq, with the first subscript stating which equation that this coefficient belongs to. So these coefficients belong to equation 1, these belong to equation 2, and these belong to equation p. And the second subscript specifies which variable the coefficient belongs to. So this belongs to the variable x1, this to x2, and this coefficient belongs to xq. And the subscript of the constant on the right hand side says which equation that the constant belongs to. Now in general, the solution to this system from S1 to SQ is an ordered tuple. So it's a sequence in the same order as the unknown variables that we want to solve for. And for the special case, when q equals 2, we call this an ordered pair. And when q equals 3, which is the 3-dimensional case, we call this an ordered triple, and so on. Let's have a geometric interpretation of the solution to a linear system with 2 unknowns. So remember that both of these each represent a line in 2D space. And in general, we have 3 types of solutions for this type of system. Noting that you can rewrite these equations in the form of y equals mx plus c, being the equation of a line. So when there's no solution, those 2 lines will be parallel, so they'll never intersect. And when we have one solution, those two lines intersect at one point. And when we have an infinite number of solutions, the lines have the same slope and the same y-intercept. So they basically overlap. Today we'll give a geometric interpretation of the solution to a linear system where we have three unknowns. So our solution here will be for the unknown variables x1, x2 and x3, which is an ordered triple. So note that these systems of equations written with three variables are the equations of a plane. So we have a constant by x plus a constant by y plus a constant by z is equal to d, which is another constant. So similar to two-dimensional linear systems, we have three groups of solutions. So the first is no solution, where we have the planes being parallel to each other. So the planes don't intersect at all. And you can also have two planes being coincident and one plane being parallel to those planes. So you'll also get no solution in this case. And even if you had one of these coincident planes intersecting both planes, so maybe you had something like this, still in this case you won't have a solution, because all the planes must intersect somewhere. And think about other scenarios where you'd have no solution. Now a case where you'll have one solution is where the three planes intersect at one point, as we can see. And you can also have infinitely many solutions. So these are examples of three planes intersecting at a common line. And remember that a plane is infinite, so this line would extend indefinitely. And here you have three coincident planes, so you'll get infinitely many solutions. And this extends generally to all linear systems, which either have no solution, one solution, or infinitely many solutions. Let's solve the following linear systems. So for this first one over here, we can use the elimination method by multiplying this second equation by 2. So that would give 2x plus 6y is equal to 0. And now if we add these two equations together, 2x gets eliminated, and we get y plus 6y is 7y, and 3 plus 0 is 3. So therefore, y is 3 on 7. And now if you substitute for y in either of these two equations, so let's just substitute in equation 2, we get x plus 3 by 3 on 7, which is 9 on 7, is equal to 0. So therefore x is minus 9 on 7. And we can write our solution as an ordered pair. And I'll leave it for you to check if this solution satisfies both equations. Now in this second example, we have three unknowns, so we need three equations to solve them. So what we'll do first is add these first two equations. So that gives 5x plus y minus y eliminates y, plus 4z is equal to 1. And now what we can do is multiply this first equation by 2 to eliminate y between equation 1 and equation 3. So what we have is 3x by 2 is 6x, plus x is 7x. And then we have 2y minus 2y is 0, and 2z minus z is z. And on the right hand side, we have 2 plus minus 2, which is 0. And now we can multiply this second equation by 4 to eliminate z. So we subtract these two equations. So we have 5x minus 28x is minus 23x. And then 4z minus 4z is 0. And 1 minus 0 is 1. So therefore, x is equal to minus 1 on 23. And then if you substitute this into one of these equations, so we'll substitute into this second equation, we have minus 7 on 23 plus z is 0. So therefore z is 7 on 23. And now we can substitute for x and z into either of these three equations. So let's just substitute in equation 3. So we have minus 1 on 23 minus 2y minus 7 on 23 is equal to negative 2. So negative 2 is minus 46 on 23. So therefore minus 2y is equal to minus 46 plus 1 is minus 45 plus 7 is minus 38 on 23. And if we divide through by minus 2, we get y is 19 on 23. So our solution is an ordered triple. Now for this linear system over here, we can see that the ratio of coefficients of x and y between both equations is the same. So if we divide the first equation by 2, we get x plus y is 7 on 2. And dividing the second equation by 5, we get x plus y is 3 on 5. So we can see that these are the equations of a line with the same slope but a different y-intercept. So the lines are parallel and therefore we have no solution. Now for this linear system with three unknowns, if we divide the first equation by 3, we get x plus y plus z is a third. And if we divide the second equation by 9, we get x plus y plus z is 2 on 9. And then the third equation is the same as the first equation. So therefore we have the equation of a plane where these two planes overlap. And given that these two equations here are conflicting, then we also have no solution. Now for this linear system over here, we can see that the ratio of coefficients between x and y is the same in both equations. So we can divide the second equation by 7, and we get x plus y is 21 on 7, which is 3. So these two lines have the same slope and the same y-intercept. So therefore, this system will have infinitely many solutions. And for this system over here, again, the ratio of the coefficients is the same in all of these equations. So we can divide the first equation by 2. So we get x minus y minus 2z is 3. And we can divide the third equation by 4. So we get x minus y minus 2z is 3. So as we can see, these are the same equations as the second. So these three are coincident planes. And therefore, you end up with infinitely many solutions. We've seen that the calculations become quite demanding for finding the solutions to linear systems with three unknowns. So the goal is to come up with a general method to solve large linear systems systematically. So to do that, we introduce matrices, which is basically a rectangular array of numbers, as we can see on the right here. And specifically, an augmented matrix is a rectangular array of numbers in a linear system with the coefficients augmented with the constants on the right hand side. So this leads to elementary row operations which are used to reduce the linear system to a simpler one at each step. So for example, an elementary row operation would be multiplying a row of this matrix by some constant. And when we multiply this row by a constant, we're basically multiplying the first equation by the same constant. So for example, if this constant were 1 on C11, then we're basically removing C11 from behind x1. And another elementary row operation is swapping two rows of this matrix. So effectively swapping the two rows means swapping the two equations. And another elementary operation is adding a constant multiplied by a row to another row. So for example, to this bottom row over here, I can add some constant multiplied by row 2 to every one of these terms in this bottom equation. And these elementary row operations are best demonstrated in an example, which we'll cover in the following video. We've solved this linear system with 3 variables using basic arithmetic operations. And now let's solve the same system by translating it to an augmented matrix. We'll have the coefficients to the left of this line and the constants on the right hand side to the right. So we're going to select the row operations to simplify the system each time. So first, we'll multiply one row or equation by a constant. So I'm going to multiply this by a third. And therefore, we obtain the following result, which is 1, 1/3, 1/3, and 1/3. So basically we've done the same thing to the first equation. Effectively isolating x. And now we'll copy this down. So the next goal would be to get rid of x from the second and third equation. So what we do is subtract 2 multiplied by row 1 from the second equation, and we subtract 1 multiplied by row 1 from the third equation. So for the second equation, we obtain 2 minus 2 by 1, which is 0, and minus 1, which is minus 3/3, minus 2/3 is minus 5/3. And 3 is 9/3, minus 2/3 is 7/3. And 0 minus 2/3 is minus 2/3. So what we've done is gotten rid of x and obtained the following coefficients for y and z. And on the right hand side we have minus 2/3. Now for the third equation, we get 1 minus 1, which is 0, minus 6/3 minus a third is minus 7/3, and minus 3/3 minus a third is minus 4/3. And minus 6/3 minus a third is minus 7/3. So again we eliminated x, and replace the coefficients of y and z. And on the right hand side we have minus 7/3. So you can see that we're simplifying our system each time. Now let's copy this down. So in the next step, we're going to get rid of the coefficient of y. So we'll multiply row 2 by minus 3 on 5. So we have 0, 1, minus 7 on 5, and 2 on 5. So consequently, our second equation is modified as follows. So we have y being isolated, minus 7 on 5 by z is equal to 2/5. And now we copy this again. So we want to eliminate y from the third equation. So we're going to add 7/3 multiplied by row 2 to the third row. So we have 0 plus 7/3 by 0, and minus 7/3 plus 7/3 is 0, and then minus 4/3 minus 7/3 by 7/5. So that would get you minus 23 on 5. And then minus 7/3 plus 7/3 by 2/5, which will get you minus 7/5. So now in the third equation, y disappears, and the coefficient of z becomes minus 23 on 5. And on the right hand side, we have minus 7 on 5. So copying the result, and now we want to remove the coefficient behind z, so we multiply the third row by minus 5 on 23. So we get 0, 0, 1, and 7 on 23. So as you can see, we've solved for z, which is 7 on 23. And now let's copy this result down again. So now we can zero out z to solve for y by adding 7 on 5, multiply by row 3 to the second row. So what we get is 0 plus 7 on 5 by 0, 1 plus 7 on 5 by 0, minus 7 on 5 plus 7 on 5 by 1, and then 2 on 5 plus 7 on 5 by 7 on 23, which gives 19 on 23. So therefore in our second equation, we got rid of z, and on the right hand side, we got 19 on 23. So we've solved for y. And I'll leave it for you to finish this off by zeroing out these terms to solve for x, and the result you should get is x is minus 1 on 23. As we've done before, by solving this system by elimination and substitution. In our previous example of a linear system with 3 unknown variables, which was solved by elementary row operations, we actually reduced this system to this form, and this is known as reduced row echelon form. So in this case, we obtained a unique solution by inspection. Now in general, we have a row echelon form which has the following properties. So if a row does not consist entirely of zeros, the first non-zero number is a 1. So here is an example where we have the first number in each row being a 1. And here is another example, and another example here. So the first number is a 1, as we can see. And here is yet another example of this property. Now the second property of the row echelon form is that rows with all zeros are placed in the bottom of the matrix. So here, for example, we have all rows of zeros, and if we suppose this matrix was something like this, then the first rule of the row echelon form is satisfied, because the first non-zero numbers are 1 in the rows that don't consist entirely of zeros, and we also have the rows with all zeros being placed in the bottom of the matrix. And the next rule is 2 successive rows that don't consist entirely of zeros. The leading one in the higher row is further to the left compared to the lower row. So as we can see, the 1 in the higher row is further to the left than the 1 in the lower row. And the same applies to the third row compared to the second. So here we also see that as we go down the rows, the 1s are further to the right. So in addition to these 3 rules, which are the properties of row echelon form, we have an additional rule for the reduced row echelon form. So in addition to these 3 rules, the additional property for a reduced row echelon form is that each column that contains a leading 1 has zeros everywhere else in that column. So as we can see, we have all leading 1s in each row of this matrix, which have zeros everywhere else in each of their columns. So similarly in the second column and the third column. So this matrix here also has leading 1s in every row, and in the first column we have all zeros, but in the second column we don't have all zeros apart from this leading 1. So therefore this matrix here is only in row echelon form, not reduced row echelon form. And similarly for this matrix, we can see that every row has a leading 1, but for the column corresponding to this one, we have -3. So there's not all zeros in that column, and therefore this matrix is also in row echelon form, but not a reduced row echelon form. And another example is that this matrix is in reduced row echelon form, because it satisfies the properties of a row echelon form where we have a leading 1 in the first row, and the rows consisting of all zeros are placed in the bottom of the matrix, and in 2 successive rows with not all zeros, the leading 1 in the higher row is further to the left. So these rows consist entirely of zeros, so this rule is satisfied automatically. And then where we have a leading 1, we have zeros everywhere else in that column, which is the reduced row echelon property. So the row echelon form is a necessary condition for a matrix to be in reduced row echelon form, but not the other way around. let's determine if these matrices are in row echelon form. So in each row that doesn't have all zeros, we have leading ones, and each one in the next row is to the right of the one in the previous row. So this matrix is in row echelon form. And further to this, we can see that the column of this leading one in the third row does not have all zeros in that column. So therefore this matrix is not in reduced row echelon form, but just row echelon form. And furthermore, assuming that this matrix is an augmented matrix that represents some linear system, in the last row we have 0x plus 0y plus 0z is equal to 1. So therefore the left hand side contradicts the right hand side, or this equation is inconsistent. So therefore this system of linear equations does not have any solutions. Now in this next example, we have leading ones in each row that doesn't contain all zeros, and the row containing all zeros is at the bottom of the matrix, and the leading one in the next row is to the right of the leading one in the previous row. So this matrix is in row echelon form. Now in each column, for each leading one, we can see the other entries in the column are 0. And for this one, the entries in the column are also 0. So therefore this matrix is in reduced row echelon form. And again, assuming this is an augmented matrix that represents some linear system, the final equation is consistent in this case. So we have 0x plus 0y plus 0z is equal to 0. And the first two equations of this system can be written as follows. So we have x plus 0y plus 5z is equal to 2. And 0x plus y minus z is equal to 3. So therefore we can write x in terms of z and y in terms of z, and therefore we can express this solution parametrically by taking z as some parameter t. So this set of parametric equations is a general solution of the system. Now for this final system, we have zeros in the last two rows and a leading one in the first row which doesn't contain all zeros. So this matrix satisfies the properties of row echelon form, and in the column of this leading one we have zeros everywhere else. So this matrix is also in reduced row echelon form. And we can see the last two equations are consistent, similar to this case. So therefore the first equation can be written as x minus 3y plus z is equal to 2. And solving for x, we can write it as 2 plus 3y minus z. And if we treat y and z as parameters, so y equals s and z equals t, we can express the solution parametrically. So we have x is 2 plus 3s minus t. So this is a general solution of the system, when we can choose different values for the parameters s and t to obtain different values for x. So there's infinitely many solutions here. Today we'll look at Gauss-Jordan elimination and compare this with Gaussian elimination. So starting with Gaussian elimination and our linear system over here, represented by this augmented matrix, then Gaussian elimination reduces this matrix to row echelon form. So to do that, we'll start by flipping the first two rows, because we want a leading one in each row. and the leading one in the bottom row should be to the right of the one in the top row. So after flipping those two equations, our matrix looks like this. And I encourage you to keep track of what happens to our system of equations as we keep doing these elementary row operations. So let's copy our result down. So as we can see, we have 1, 0 and 0, 1 in the first two rows, which satisfies the properties of row echelon form. And we need to do the same with the third row. So we'll try to zero out these two by subtracting 2 multiplied by row 1. So in the third row, we have 2 minus 2 by 1, 2 minus 0, 4 minus 2 by 2, and 2 minus 2 by 5. So 2 minus 10 is minus 8. And then we have 1 minus 2 by 3, which is negative 5. And now we'll keep going. So we'll now try to zero out this 2 by subtracting 2 by row 2 from the third row. So let's just do this for the entire third row. So we have 0 minus 2 by 0, 2 minus 2 by 1, and then 0 minus 2 by 2 gives negative 4. And minus 8 minus 2 is negative 10, and minus 5 minus 10 is minus 15. So as we can see, this 0 has been flipped. And now we're going to try to get a leading one in the third row, so we multiply this by minus a quarter. So 0 and 0 by negative a quarter will remain 0. So only these three terms are going to change. So minus 4 by negative a quarter is 1. Minus 10 by minus a quarter is 5 on 2. And minus 15 by negative a quarter is 15 on 4. So up to here, we see that we have row echelon form, because we have a leading one in each row, and each one in the next row is to the right of the one in the previous row. So this process, by achieving row echelon form using elementary row operations, is called Gaussian elimination. So this is basically the forward pass. And now let's copy our resulting matrix to do the backward pass. So I'll just do this up here, and we'll copy it again down here. So in the backward pass, we want to achieve reduced row echelon form. So effectively we want zeros where these two entries are, given that we want zeros in the columns of the leading ones. So we'll start off by subtracting 2 multiplied by row 3 from this row, because given these zeros, we're not going to modify these previous entries. So our second row is going to look like this. So we have 0 minus 2 by 0, 1 minus 2 by 0, and then 2 minus 2 by 1, and then 1 minus 2 by 5 on 2, or 1 minus 5 is negative 4. And then we have 5 minus 2 by 15 on 4, or 5 minus 15 on 2. So we can multiply this 5 by 2 on 2, and we get 10 minus 15 is negative 5 on 2. And now let's do the next operation in the next step. So to make this 2 a 0, we'll again minus 2 by row 3 from the first row, because we're not going to modify these two entries given these zeros in the third row. And let's put our result down here. So we have 1 minus 2 by 0, 0 minus 2 by 0, 2 minus 2 by 1, and then 5 minus 2 by 5 on 2, which is 0, and then we have 3 minus 2 by 15 on 4, or 3 minus 15 on 2. So if we multiply 3 by 2 on 2, we get 6 minus 15, which is minus 9 on 2. So as we can see now, this matrix is in reduced tri-echelon form, which I'll write RE for a shortcut. And this backward pass, where we're zeroing out these elements above this diagonal, plus the forward pass, is called Gauss-Jordan elimination. So what we've done is reduced our system to x1 plus 0x2 plus 0x3 plus 0x4 is equal to minus 9 on 2. And then we have 0x1 plus 1x2 plus 0x3 minus 4x4, and that's equal to negative 5 on 2. And then in our third equation, we have 0x1 plus 0x2 plus x3 plus 5 on 2 x4 is equal to 15 on 4. So our solution to this system is x1 is minus 9 on 2. And we can see that in the second equation, we have a free variable. So we can write this as x2 is minus 5 on 2 plus 4x4, and x3 is 15 on 4 minus 5 on 2 x4. So if we denote x4 is equal to t, then we express our solution parametrically, and thereby we're going to have infinitely many solutions, because x2 and x3 can be calculated using different values for the parameter t. And I encourage you to select different values for this parameter and verify that the different solutions you get satisfy this system of equations by substituting for x1, x2, x3 and x4. Homogeneous linear systems are special types of linear systems where the right hand side is all zeros. So therefore all homogeneous systems have a solution where all the variables are 0. And therefore homogeneous linear systems are all consistent. So this is called a trivial solution. And due to this trivial solution, there's only two types of solutions for homogeneous linear systems. So one type of solution is only the trivial solution, or infinitely many solutions in addition to the trivial solution. So this can be seen for the special case where you have a homogeneous linear system of two variables. So for example, if we had x plus 2y, and this is homogeneous, so it must be 0 on the right. So if we write the equation of this line in the explicit form, then we can say that the y-intercept is 0 for all of these two variable homogeneous linear systems. So there'll always be one trivial solution as these lines intersect at the origin, and infinitely many solutions if the lines overlap. Now generally, if the system has more unknowns than equations, then the homogeneous linear system definitely has non-trivial solutions. So for example, in reducing this homogeneous linear system to reduced tri-echelon form, we have the following reduced form. So x1 is 0, then we have x2 minus 4x4 is 0. And finally, x3 plus 2x4 is 0. So if we write the leading variables in terms of the free variable x4, and in a parametric form, we have x4 is equal to the parameter t, and therefore we can express this solution parametrically. So as we can see, we have the trivial solution where t is equal to 0, and note that x1 is also 0, or infinitely many solutions for other values of the parameter t. So as you can imagine, elementary row operations don't affect the column of zeros. So effectively, in reduced row echelon form, we have all zeros on the right hand side. So the reduced row echelon form is also homogeneous, just like the original system. And if we had a row of zeros here at the bottom, this would impose no restrictions on the unknowns. So noting the trivial solution, if this row were all zeros, then what we'd have is 0x1 plus 0x2 plus 0x3 plus 0x4 is 0. So this would impose no restrictions, because we have 0 on the left and 0 on the right, no matter what the values of the unknown variables. So effectively, the reduced row echelon form either has the same number of equations as our original system, or fewer. So for example, if this row turned out to be all zeros. For linear systems that are quite large, it's more efficient to reduce the augmented matrix to row echelon form, which is the Gaussian elimination step, and then follow this by back substitution to solve the system, rather than doing the Gauss-Jordan elimination to get the system in reduced row echelon form. So consider our previous example, where we reduce the augmented matrix to row echelon form. So our system is x1 plus 2x3 plus 5x4 is equal to 3. And then we have x2 plus 2x3 plus x4 is equal to 5. And then we have x3 plus 5 on 2x4 is 15 on 4. So the first step is working from this row echelon form of our system and solving the equations for the leading variable. So our leading variable is x1. So we have 3 minus 2x3 minus 5x4. And in the next equation, our leading variable is x2. So we have 5 minus 2x3 minus x4. And then x3 is 15 on 4 minus 5 on 2 x4. And now we start from the bottom and substitute each equation into the equations above it. So therefore x1 is equal to 3 minus 2 by x3, which is 15 on 4, minus 5 on 2x4, minus 5x4. So we can see that this simplifies to 3 minus 2 by 15 on 4, which is 3 minus 15 on 2, and 3 is 6 on 2. So what we get is minus 9 on 2, and then we have plus 5x4 minus 5x4 is 0. So we solved for x1. And substituting x3 into x2, we get 5 minus 2 by x3, which is 15 on 4, minus 5 on 2 x4, and then minus x4. So what we have is 5 minus 15 on 2, so that will be 2 by 5 on 2, which is 10 minus 15 on 2, or minus 5 on 2. And then we have 5x4 minus x4 is 4x4. And this is our final step, because we can't really substitute x2 in x1. So now we'll write down our solution so far. And the final step is to assign arbitrary values to the free variables. So in this case, we have x4 being the free variable. So we'll call that the parameter t, where x4 is equal to t. And therefore we can assign arbitrary values of t to get infinitely many solutions. And this is the same result we got using Gauss-Jordan elimination. As we've seen, obtaining a solution to a large linear system can get tedious, and therefore we used augmented matrices to do that. But in general, a matrix is a rectangular array of elements. So for example, we stored the coefficients of a linear system in the matrix, and these numbers are called the entries in the matrix. Now the size of the matrix is the number of rows, which is p in this case, by the number of columns being q. So each row of this matrix represents the constants in each linear equation that we see. Now vectors, on the other hand, are special types of matrices with either one row or one column. So for example, a column vector here has multiple rows and one column, whereas this row vector has multiple columns and one row. And we'll see that when we multiply this matrix of coefficients by this column vector, we're going to get these equations. And the column vector on the right hand side represents these constants on the right. Now we can also use compact notation to represent matrices. So in the first notation, where we need to know the size of the matrix, we have the matrix C with entries in row I and column J. And we can write the number of rows by the number of columns here. And here we have the entries in row I and column J for matrix C. And here is another compact representation for our matrix C with entries in row I and column J. Now a square matrix, for example here, where we have the number of rows being equal to the number of columns, is a special type of matrix, which we'll look at further later on. So this type of matrix has the following elements on the diagonal. So the entry in row 1, column 1, the entry in row 2, column 2, and the entry in row 3, column 3. And by inverting a matrix, we can solve systems with many unknown variables. Let's look at the basic matrix operations, and one of those is equality. So two matrices are equal if they have the same size, so the same number of rows and the same number of columns, and their corresponding entries are all equal. So one example here is that matrix A is equal to matrix B because they have the same number of rows and columns, and the entries in both matrices in the corresponding row and column are equal. So we have 1 is equal to 1, 0 is 0, minus 2 is equal to minus 2, and 4 is equal to 4. Now matrix B is not equal to matrix C, because B has 2 columns and C has 3 columns. Now the next basic operations are addition and subtraction. So again, the matrices must have the same size, otherwise you cannot add or subtract them. So as we can see, A plus B is valid because both matrices have the same number of rows and columns. So if we added these matrices together, we just sum the corresponding entries. So 1 plus 1 is 2, minus 2 plus minus 2 is negative 4, 0 plus 0 is 0, and 4 plus 4 is 8. And similarly, B and D have the same size, so we can also do B minus D. So that'll be 1 minus 1 is 0, minus 2 minus negative 2 is 0, 0 minus x is negative x, and 4 minus 4 is 0. So we can't sum A and C, because A has 2 columns and C has 3 columns, and we can't subtract C from B for the same reason. Now the next basic operation is the scalar product, which is multiplying a scalar or a number by a matrix. So basically multiplying the scalar by the matrix is the same as multiplying the scalar by every entry in the matrix. So for example, 2 multiplied by A will give 2 multiplied by 1 is 2, 2 by negative 2 is negative 4, 2 by 0 is 0, and 2 by 4 is 8. And a special case is multiplying negative 1 by a matrix, which simply negates the matrix. So effectively minus A is the same as negating all those elements. So I have minus 1, minus minus 2, minus 0, and minus 4. Now our final basic operation is the trace of a matrix, which is written as follows, and this is only defined if A is a square matrix. So effectively the number of rows is equal to the number of columns, and it's the sum of the entries on a diagonal. So effectively the trace of matrix A is 1 plus 4, which is 5. Today we'll look at matrix multiplication and where it's defined or not defined. So if we consider 2 matrices A and B, which have a number of rows by a number of columns, then for us to be able to multiply these 2 matrices, the number of columns in matrix A must be equal to the number of rows in matrix B. And the resulting matrix has the same number of rows as matrix A and the same number of columns as matrix B. So for example, this first matrix has 2 rows by 3 columns, and this second matrix has 3 rows by 1 column. So the number of columns in A is equal to the number of rows in B, so this multiplication is valid, and our resulting matrix will have 2 rows by 1 column. And for this example here, we have 3 rows and 2 columns in matrix A, and 2 rows and 2 columns in matrix B. So the number of columns in A is equal to the number of rows in B, so this multiplication is valid, and our resulting matrix will have 3 rows and 2 columns. And in this example, we have a 3 by 3 matrix multiplied by a 1 row by 3 column row vector, So the number of columns in A is not equal to the number of rows in B. So this matrix multiplication is not valid. Now let's do a couple of examples. So I'm going to copy this over here. So to multiply these matrices together, the first entry of the resulting matrix is in row 1, column 1. So what we do is multiply row 1 of this matrix by column 1 of this matrix, which only has one column. So that would be 1 multiplied by 1 plus 2 multiplied by 4 plus negative 1 multiplied by 2. So that gives 9 minus 2, which is 7. And then to get the element in row 2, column 1 of the resulting matrix, we multiply row 2 of this matrix by column 1 of this matrix. So that would be 1 by 1 plus 3 by 4 plus 0 by 2. So 1 plus 12 is 13 plus 0 is 13. So this here is our resulting matrix, which, as we said, is a 2 by 1. And now let's do this example. So as we determined, our resulting matrix from this multiplication will have 3 rows and 2 columns. So to get the entry in row 1, column 1, we multiply row 1 of this matrix by column 1 of this one. So that will be 1 multiplied by 2 plus 3 multiplied by 1. So 2 plus 3 is 5. And the entry in row 2, column 1 is obtained by multiplying row 2 of this matrix by column 1 of this matrix. So 2 by 2 is 4 plus 7 by 1 is 11. And you'll see a pattern here. So we have the third row multiplied by the first column will give us this entry over here. So 4 by 2 is 8 plus 2 is 10. And then if we multiply row 1 by column 2, we'll get this entry over here in row 1, column 2 of the resulting matrix. So 1 by 1 is 1 plus 3 by 4 gives 13. And then the second row by the second column gives this entry in the second row and second column of the resulting matrix. So 2 by 1 is 2 plus 7 by 4, which is 28, gives 30. And finally, row 3 by column 2 gives this final element over here. So 4 by 1 is 4 plus 2 by 4 is 8, gives 12. So note that matrix multiplication is not commutative, because if we reverse this multiplication, we'd have a 2 by 2 multiplied by a 3 by 2. So the number of columns in A will no longer be equal to the number of rows in B. And therefore this matrix multiplication would not be valid. We can partition matrices in different ways to simplify solving different problems. So for example, we can partition matrix A into a left-hand matrix, a row vector, and so on. And the matrix can be partitioned in any way. Now one thing we recognize is that partition matrices can help us visualize matrix multiplications using vectors. So remember that when we multiplied two matrices, we had the number of columns in A being equal to the number of rows in B, and our resulting matrix will have the same number of rows as A by the number of columns in B. So in matrix multiplication, we saw that we multiply the row in matrix A by the column in matrix B, that corresponds to the entry in the resulting matrix. So if we wanted the resulting entry in row 1 and column 1 of the matrix, we multiply row 1 by column 1 of these two matrices. So given that this first entry is row 1 in A by column 1 in B, and this second entry is row 2 in A by column 1 in B, and this third entry here is row 3 in A by column 1 in B, then if we designate column 1 in B as the column vector B1, with the entries in the matrix B11, B21, and B31, then what we're essentially doing to get the entries in column 1 is multiplying this entire matrix A by this column vector B1. So that gives the entries in column 1 of the resulting matrix. And similarly, if we designate the entries in column 2 as a column vector B2, then multiplying the entire matrix by this column vector is going to give the entries in the next column of that matrix. And you can see a pattern here. So the matrix A by the column vector B3 will give the entries in the third column of the resulting matrix. So as we can see, this is the same thing as putting B1 to B3 in a row vector. So that's exactly the same as this matrix B, and we'll just multiply A by B. So really have a think about this. Now alternatively, we can designate the entries in A as row vectors. So we have the row vector in row 1 with the following entries. So if we multiply this row vector in A by column 1 in B, we get this entry in our resulting matrix. And multiplying this row vector in A by the second column of B gives this entry. And multiplying this row vector by the third column in B gives this entry over here. So essentially multiplying this row vector in the first row by the entire matrix B gives the entries in the first row of the matrix. And similarly, the row vector in row 2 of matrix A multiplied by this matrix B is going to give the entries in the second row. So here we're essentially getting row vectors representing each row of the resulting matrix. And similarly, the row vector in row 3 multiplied by the matrix B is going to give the entries in the third row of the resulting matrix. So essentially that's the same as representing matrix A as this column vector of row vectors and multiplying it by B, which is the same as multiplying matrix A with matrix B. Suppose we have matrices M1 to Mn all having the same size, and scalars or numbers from C1 to Cn. Then if we multiply each constant by the corresponding matrix and sum the results together, then this here is called a linear combination of these matrices with the following coefficients. So if you consider a product of this matrix of coefficients, which we'll call A, by this vector, then remembering our matrix multiplication, so we have each row of the matrix by the vector, gives the corresponding row in our resulting matrix. So C11 by x1, C12 by x2, and so on gives the first row. So as we can see, we can express this as a linear combination of the scalar x1 multiplied by the first column in the matrix plus x2, and that's multiplied by the second column in the matrix. And so on, up to xq, multiplied by the final column, which has entries c1q, c2q, and so on, down to cpq. The transpose of some matrix A is obtained by interchanging the rows and columns of A. So if we look at this at the matrix entry level, we have the entry in A at row I and column J, and the entry in row I and column J of the transpose is equal to the entry in matrix A at row J and column I. So for example, if we take the transpose of this matrix A, we basically interchange the rows with the columns. So the first row becomes the first column, and the second row becomes the second column. So for example, the entry in a transpose of A in row 2 column 1 should be equal to the entry in A in row 1 and column 2. Now for the special case of a square matrix, if we take the transpose of B, then the elements on the main diagonal remain the same. So for our square matrix here, all we do is swap the symmetric elements above and below the diagonal, according to our equation here for the transpose. So the element in row 1 column 2 is swapped with the element in row 2 column 1. And the element in row 1 column 3 is swapped with the element in row 3 column 1. And 2, 3 is swapped with 3, 2. And the transpose of our matrix C with a single row, which is a row vector, becomes a column vector. So we have the entry in row 1 column 1 being the same, and the entry in row 1 column 2 becomes the entry in row 2 column 1 in our transpose. And the entry in row 1 column 3 becomes the entry in row 3 column 1 in the transpose. Recall that in real arithmetic, we had some real number by its reciprocal, which is the same as its reciprocal by the real number, which gave 1. So r to the minus 1 was called the multiplicative inverse of r. Now similarly, when we look at matrices, we have a matrix M by its inverse is the same as its inverse multiplied by M, which should give the identity matrix. So the identity matrix has all 1s on a diagonal and 0 everywhere else. So for example, for this 3 by 3 matrix, we have 1s on a diagonal and all 0s otherwise. Now if we can find this matrix here, that when multiplied by M gives the identity matrix, then M is a square matrix and invertible, or non-singular. Otherwise, if no such inverse can be found, then the matrix M is said to be singular. So generally, a singular matrix has rows or columns of zeros. So here is an example. So suppose we have some matrix multiplied by this singular matrix. Then remember, we can represent a matrix using column and row vectors. So for example, this matrix product can be written as n multiplied by this row vector of column vectors of S. So we can represent the first column in S as S1 and the second column as S2. And this was the same as taking n inside the matrix. So therefore what we'll get is a column vector of zeros here in the resulting matrix, and therefore this resulting matrix cannot be an identity matrix. So the inverse does not exist for this singular matrix. Now a method we can use to find the inverse of a 2 by 2 matrix, so 2 rows and 2 columns. So if we take the inverse, what we do is take the reciprocal and we multiply the diagonal elements and subtract them from each other. So what we get is A multiplied by D minus B multiplied by C. And we multiply this by a 2 by 2 matrix where we flip A and D and negate B and C. So let's try this out by calculating the inverse of M. So 1 over A multiplied by D minus B multiplied by C. So we swap A and D and negate B and C. So what we end up with is 1 on 10 multiplied by this matrix. So that would give 4 on 10, or 2/5, minus 3 on 10, 2 on 10, which is 1 on 5, and 1 on 10. So we're just multiplying a scalar by a matrix. And now if we want to verify that this is the inverse of M, then we just multiply M by the inverse. So M had the following entries, and the inverse had the following entries. So to obtain an entry in row 1, column 1, we multiply row 1 by column 1. So that'll be 1 by 2/5 plus 3 by 1/5. And row 1 by column 2 gives the next entry in row 1. So we have 1 by minus 3/10 plus 3 by 1/10. And then minus 2 by 2/5 is minus 4/5 plus 4 by 1/5. And finally we have minus 2 by minus 3/10, which is 6/10, plus 4 by 1/10, which is 4/10. So as we can see, this results in 1, 0, 0, 1, being a 2 by 2 identity matrix. And we'll develop a general method to calculate the inverse for larger matrices. If we take the product of two matrices, M and N, and take their inverse, that should be the same as taking the inverse of N and multiplying it by the inverse of M. So if you want to show this, we can multiply the matrix that results from the product between M and N, and then multiplying this by the inverse should give the identity matrix. So therefore, if we have Mn, and then replace a second term with n to the minus 1 by m to the minus 1, assuming that this is the inverse of Mn. And now we can use the associative law for matrix multiplication. So we can take M and multiply that by n to the minus 1, and then multiply by m to the minus 1. And therefore this is the identity matrix, and m to the minus 1 by the identity matrix is the same as m to the minus 1. So what we get is m by m to the minus 1, and the product of a matrix with its inverse is the identity matrix. And we can show why this works with an example. So we have the matrix M and the matrix N, and I encourage you to verify that this is the inverse of M and this matrix is the inverse of N. We're using the previous method that we used for inverting 2 by 2 matrices. And we've also calculated the product of M and N and then calculated its inverse. So as an exercise, have a go at multiplying the inverse of N by the inverse of M, and you should get this result over here. And post any questions you have in the comments. The powers of a matrix are useful when we have diagonal matrices, such as this one over here, with non-zeros for the diagonal elements only. So for example, if we take m to the power of 3, it's m multiplied by m multiplied by m. And if you multiply this out, you'd get 8s on the diagonal, or 2 cubed, and zeros elsewhere. So more generally, m to the power of some exponent is m multiplied by m e times. And m to the 0, being a special case, is the identity matrix. So recall that this identity matrix would have 1s on the diagonal and 0 everywhere else. Now if the matrix is invertible, then m to the power of minus e is the same as the inverse of m to the power of e. So that's representative of the inverse multiplied by itself e number of times. And because the definitions for matrices are parallel for real numbers, then the laws of non-negative exponents hold. So for example, if we have m to the power of e multiplied by m to the power of f, then we keep the base and sum the indices. And again, provided the inverse of a matrix exists, if we take the inverse of the inverse, then that gives back m. And if we take the inverse of m to the power of the exponent, then that's the same thing as m to the minus e, which is the inverse to the power of e. And taking the inverse of a scalar multiplied by the matrix is the same as multiplying the reciprocal of the scalar by the inverse of the matrix. And in a similar way to polynomials, we have the binomial expansion of m plus n, which is m to the power of 2 plus mn plus nm plus n squared. So this is not exactly identical to a polynomial expansion, because generally the matrix product is not commutative, but for matrices that commute, such as diagonal matrices, this term here would be 2mn. We can use Gauss-Jordan elimination to invert a square matrix of any size, and the basic idea is that the same sequence of row operations that reduces M to the identity matrix will transform the identity matrix to the inverse of M, provided the inverse exists. So this is best demonstrated in an example. So we place the matrix M and the identity matrix in an augmented matrix and perform the elementary row operations on both matrices simultaneously. So first we want zeros below the diagonal, so we start with column 1 and subtract row 1 from row 2, and we subtract 3 by row 1 from row 3. So let's start with row 2. So 1 minus 1 is 0, 3 minus 2 is 1, 2 minus 3 is negative 1, and 0 minus 1 is minus 1, 1 minus 0 is 1, and 0 minus 0 is 0. And now row 3, 3 minus 3 is 0, 2 minus 6 is minus 4, 1 minus 9 is minus 8, and 0 minus 3 is negative 3, 0 minus 0 is 0, and 1 minus 0 is 1. And now we'll zero out the remaining element below the diagonal. So we'll add 4 by row 2 to row 3. So noting that this first element here, plus 4 by 0 is still 0. So we don't modify it. So we have minus 4 plus 4 is 0. Minus 8 minus 4 is minus 12. Minus 3 minus 4 is minus 7. 0 plus 4 is 4. And 1 plus 0 is 1. And now we want 1 on the remaining diagonal entry, so we multiply row 3 by minus 1 on 12. So this element becomes 1, and we get 7 on 12, minus 4 on 12, or minus a third, and minus 1 on 12. And now we'll zero out the elements above the diagonal. So starting with the far right column, we're going to add row 3 to row 2, and subtract 3 by row 3 from row 1. So starting with row 2, we have minus 1 plus 1 is 0, minus 1, which is minus 12 on 12, plus 7 on 12 is minus 5 on 12. And then 1, which is 3/3, minus a third is 2/3. And 0 minus 1/12 is minus 1 on 12. And now for the first row, we have 3 minus 3 is 0, 1, which is 12 on 12, minus 3 by 7, which is 21 on 12, gives minus 9 on 12. And we have 0 minus 3 by minus a third is 1. And 0 minus 3 by negative 12 is 1 on 4. And to zero out the remaining element above the diagonal, we'll subtract 2 by row 2 from row 1. So 2 minus 2 is 0. Minus 9 on 12 plus 10 on 12 gives 1 on 12. And 1, which is 3/3, minus 4/3 gives minus a third. And then we have 1/4, which is 3 on 12, plus 2 on 12 gives 5 on 12. And you can verify that this is actually the inverse of our matrix M by multiplying them together, which should give you the identity matrix. So note that if the reduced row echelon form of our matrix M had a row of zeros, then our matrix would not be invertible. Suppose we have a system of linear equations where we represent the coefficients of our variables in the matrix A, and we place our variables in a column vector. And also our constants on the right hand side in a column vector. So therefore this system can be written using our matrix of coefficients by x equals b. Now if the inverse of A exists, which we've shown previously using Gauss-Jordan elimination, and recall A was a square matrix with the same number of rows as the number of columns, then the system of equations Ax equals b has exactly one solution. So if we multiply both sides by the inverse of A, which we've shown to exist, then this equation becomes x is equal to the inverse of A by b. So for each vector b of these constants on the right hand side, there's a unique solution. And I encourage you, as an exercise, to use matrix multiplication to evaluate the product on the right hand side to obtain x, which contains our unknown variables. A square matrix where the entries that are off the main diagonal are all 0 is called a diagonal matrix. So here are other examples of diagonal matrices where all the off diagonal entries are 0. And a diagonal matrix is invertible if and only if all of its diagonal entries are non-zero. So we can see that the inverse is easily computed, where we put the diagonal matrix and the identity matrix in an augmented matrix, and we aim to obtain 1s on the diagonal to reduce this to the identity matrix. So this is done by multiplying the second row by 1/3 and the third row by 1/2. So therefore what we obtain are 1s on the diagonal, and then this becomes 1/3 and this becomes 1/2. And therefore this matrix is the inverse of A. So if we had 0 on a diagonal, then we could not reduce A to an identity matrix, and therefore the inverse would not exist. So really think about this. Now the powers of a diagonal matrix are easy to calculate. So if n is a positive integer, so we effectively raise each diagonal element to the power of n. So we can see this by multiplying A with itself several times. So try to multiply these two matrices together, and you'll get 1 squared, 3 squared, and 2 squared on the main diagonal, with the off diagonal elements being zeros. And if you keep repeating this n times, you'll get a to the power of n, where n is a positive integer. Triangular matrices are square matrices with special properties. So an upper triangular matrix has all zeros below the diagonal, and a lower triangular matrix has all zeros above the diagonal. Now the transpose of an upper triangular matrix is a lower triangular matrix. So for example, the entry in row 1 column 2 gets swapped with the 0 in row 2 column 1, and the entry in row 1 column 3 gets swapped with a 0 in row 3 column 1, and so on. So effectively the zeros below the diagonal get swapped with the entries above the diagonal. And similarly, the transpose of a lower triangular matrix is an upper triangular matrix. Now if we multiply two upper triangular matrices, we get an upper triangular matrix. And if we multiply two lower triangular matrices, we get a lower triangular matrix. So try to verify this by multiplying U with U and L with L. Now the inverse of a triangular matrix only exists if all the entries on the diagonal are not equal to 0. And the inverse of an upper triangular matrix is also an upper triangular matrix, and the inverse of a lower triangular matrix is also a lower triangular matrix. So let's quickly invert this upper triangular matrix, which we've augmented with the identity matrix. So using Gauss-Jordan elimination, we want ones on the diagonal, so we multiply the second row by a third, the third row by a half, and the fourth row by a half. So we get 1, 1, and 1 on a diagonal, and this entry becomes 1/2, and we get 1/3, 1/2, and 1/2. And now we want to zero out the entries in the far right column. So we subtract row 4 from row 1, and we subtract half of row 4 from row 3. So that gives us 0 and 0. And the only non-zero entry in row 4 is this one. So we get -1/4 and -1/2. And now to zero out this entry, we add row 3 to row 1. So this becomes a 0, and this becomes a half, and -1/2 -1/4 is -3/4. And finally, to zero out this entry, we subtract 2 by row 2 from row 1. So this will be a 0, and this is the only non-zero entry in row 2. So we get -2/3 over here. So as we can see, the inverse of U is upper triangular. And you can multiply them together to verify you get the identity matrix. A square matrix is symmetric if it's equal to its transpose. So in other words, the entries in row I, column J, are equal to the entries in row J, column I. So examples can be seen over here, where if you transpose this matrix, you get the same matrix. So row 2, column 3 is equal to row 3, column 2, and so on. So we can see that all diagonal matrices are symmetric due to having all zeros off the diagonal. So you can imagine that if you add two symmetric matrices or subtract them, then the result will be a symmetric matrix. And if you multiply a symmetric matrix by a scalar, the resulting matrix will also be symmetric. And in general, the products of symmetric matrices are not symmetric, but only in a special case where S1 and S2 commute. And if a symmetric matrix S is invertible, then the inverse of this matrix is also symmetric. The determinant can be used to develop a specific equation to calculate the inverse of a matrix. So if we recall the inverse of a 2 by 2 matrix, this was only defined if this expression in the denominator was not 0. And this is called the determinant of our 2 by 2 matrix. So therefore we can write the inverse of this matrix as 1 over the determinant of the matrix, and that was multiplied by this matrix where we flip these two entries and then we negate these two entries, where the determinant of the matrix A is a scalar and can be written as follows. Now the determinant of a 1 by 1 matrix, which is a matrix with one entry, is equal to that entry. So following on from this definition, we define a minor of a matrix for the entry in row I column j as mij as the determinant of the submatrix, which will denote as, after row I and column j are removed from the matrix. So for example, the minor matrix of the entry in row 1, column 1 of our matrix A is equal to the entry in row 2 and column 2. Basically, we remove row 1 and column 1 and we're left with this entry. And the cofactor of the entry in row I, column j is minus 1 to the power of I plus j multiplied by the minor in row I, column j. So in our case, the cofactor of the entry in row 1, column 1 is minus 1 to the power of 1 plus 1 by the minor, which gives the same result. So effectively, when I plus j is odd, then you get a negative sign behind the minor. So using these definitions of a minor and cofactor, the determinant of a matrix is a cofactor expansion along a row or column where we multiply every entry in the row or column that we choose by the corresponding cofactor, and the result will always be the same. So for example, if we do a cofactor expansion along row 2 of this matrix, so we can determine the minor of the entry in row 2, column 1. So basically removing row 2 and column 1, we're left with A12. And the minor of the entry in row 2, column 2 is A11. So basically removing row 2 and column 2, and that's what we're left with. And therefore the cofactor of the entry in row 2, column 1 is minus 1 to the power of 2 plus 1, which will give a negative result. So that will be minus A12. And the cofactor of the entry in row 2, column 2 is minus 1 to the power of 2 plus 2, which will be positive. So that'll be A11. So to get the determinant of A, we're doing a cofactor expansion along row 2 here. So we have the entry in row 2, column 1 multiplied by its corresponding cofactor. So that will be multiplied by minus A12. And then we have A22 multiplied by its corresponding cofactor, which is a positive. So that's effectively the same as the determinant of A in the denominator here. So you could have done a cofactor expansion along column 1, column 2, row 1 and row 2, and you'll get the same result. So try to verify this. Now let's find the determinant of this matrix A, and here we'll do a cofactor expansion along column 3. So the minor of the entry in row 1 column 3 is the determinant of the submatrix after row 1 and column 3 are removed. So that will be this submatrix over here. So we take the determinant of 1, 3, 3, 2. So as we've seen for a 2 by 2, that's equal to 1 by 2 minus 3 by 3, which gives negative 7. And similarly, the minor of the entry in row 2 column 3 is the determinant of the submatrix with row 2 and column 3 removed. So that leaves this submatrix with the following entries, being 1, 2, 3, 2. So the determinant of this submatrix is 1 by 2 minus 2 by 3, which is minus 4. And the minor of the entry in row 3 column 3 is the determinant of the submatrix with row 3 and column 3 removed. So what we're left with is the following submatrix. So the determinant of this submatrix is 1 by 3 minus 2 by 1, which is 1. So the cofactor of the entry in row 1 column 3 is minus 1 to the 1 plus 3, which is 4, multiplied by the minor, which remains as minus 7. And similarly, the cofactor of the entry in row 2 column 3 is minus 1 to the 2 plus 3, multiplied by negative 4, which makes this positive. And the cofactor of the entry in row 3 column 3 is minus 1 to the 3 plus 3, multiplied by 1, which is 1. So therefore the determinant of our matrix is the sum of each entry in this column multiplied by the corresponding cofactor. So we have the entry in row 1 column 3, which is 3, multiplied by its cofactor, plus the entry in row 2 column 3, multiplied by its cofactor, plus the entry in row 3 column 3, multiplied by its corresponding cofactor. So that gives a determinant of minus 12 for this 3 by 3 matrix. And note that we could have chosen any row or any column to do the cofactor expansion, and that'll give you the same result, which I'll leave for you to verify. For large matrices, it is not efficient to do a cofactor expansion. So a more efficient method is to use Gaussian elimination while operating directly on a determinant. And we'll cover some general rules as we demonstrate the process. So the determinant of A is a scalar, and we represent it as follows. So we have the entries of the matrix between two vertical lines. And what we aim to do is get this in row echelon form using Gaussian elimination. So in the first step, we're going to flip these two rows to get a 1 on a diagonal. So that gives the determinant of A. So we have 1, 3, 2 in the first row, and 0, 2, 3 in the second row. So a row flip negates the determinant. And then we want to get zeros below the diagonal, so we subtract 3 times row 1 from row 3. So let's copy our result down here. So we get 3 minus 3 is 0, 2 minus 9 is minus 7, and 1 minus 6 is minus 5. So adding a scalar multiplied by a row to a row does not alter the determinant. So let's copy our result down. And let me just remove this here. So finally, we add 7 on 2, multiplied by row 2 to the third row. So as we can see, this 0 doesn't get affected. Then we have minus 7 plus 7 on 2 by 2 is 0. And minus 5, which is minus 10 on 2, plus 7 on 2 by 3, which is 21 on 2. So that gives 11 on 2 over here. And again, adding a scalar by a row to another row does not alter the determinant. And you can verify this by calculating the determinant of each matrix that results from each row operation that we did. And now we can do some factoring to put all ones on a diagonal. So when we do factoring, we scale the determinant accordingly. So for example, if we take out 2 from the determinant to factor row 2, what we get is 2 by 1 is 2, and 2 by 3 on 2 is 3. And similarly, we're going to factor 11 on 2, so let me just make a bit of space here. So factoring 11 on 2 in the third row, we get 11 on 2 by 1 over here. So we scale the determinant accordingly when we factor a row. So therefore this matrix now is in row echelon form, and the determinant of a diagonal matrix is obtained by multiplying the entries on a diagonal. So have a go at doing this. So the determinant of our upper diagonal matrix is 1, and the determinant of A is therefore minus 2 by 11 on 2 by 1. So the determinant of A is minus 11. And I encourage you to verify this by doing a cofactor expansion on this matrix. We can find the inverse of a matrix using the adjoint matrix. So assuming the matrix A is invertible, we have the inverse is 1 over the determinant multiplied by the adjoint matrix of A. And the adjoint matrix is the transpose of the cofactor matrix. So let's find the cofactors. So we have the cofactor of the entry in row 1, column 1 being minus 1 to the 1 plus 1, and that's multiplied by the determinant of the minor, with the minor being composed of the entries in this matrix, with row 1 and column 1 removed. So the determinant of this minor is 3 by 1 minus 2 by 2, which is minus 1. And let's do this for the entry in row 1 and column 2. So the cofactor is minus 1 to the 1 plus 2 by the determinant of the minor, which is composed of the entries that are not in row 1, column 2. So the determinant of this minor is 1 by 1 minus 2 by 3. So that would give minus 5, and minus minus 5 is plus 5. And if we continue this process, you'll get the following cofactors. And now we can put these resulting cofactors in a cofactor matrix. So we have C11, C12, C13, and then C21, C22, C23, and C31, C32, and C33. So the transpose of this matrix is the adjoint matrix of matrix A. So to transpose this, we have -1, 5, and -7, and then 4, -9, 6, and then -5, 3, -2. So basically we put the rows of the cofactor matrix as columns in the adjoint matrix. Now the determinant of matrix A is the sum of the products of the entries in a row or column of this matrix by its corresponding cofactors. So let's suppose we use row 3, then we have 3 by -5 plus 2 by 3 and plus 1 by -2. So that gives -15 plus 6 is -9, -2 is -11. So therefore the inverse of A is the reciprocal of the determinant of A by the adjoint matrix. So we just divide each entry by -11. Cramer's rule states that if we have a system of linear equations with n unknowns and the determinant of the coefficient matrix is not equal to 0, then the system has a unique solution, being x1 is equal to the determinant of the matrix with column 1 replaced with this right hand vector b on the determinant of the coefficient matrix, and similarly x2 is the determinant of matrix A2, where A2 is the matrix with column 2 replaced with this vector b, and that's divided by the determinant of A, and this continues on and on to the nth unknown, which is equal to the determinant of matrix AN, where the nth column is replaced with the vector b on the determinant of the coefficient matrix A. So let's show this for our system here with a 3x3 coefficient matrix. So first we determine if this system has a unique solution. So to do that, you calculate the determinant of matrix A. And we'll do a quick cofactor expansion of row 1. So we have 1 by the determinant of the minor, which is 3 by 1 minus 2 by 2. And we subtract 2 by the determinant of the minor, so that'll be 1 by 1 minus 2 by 3. And then we add 3 by the determinant of the minor, so that'll be 1 by 2 minus 3 by 3. So that would give you minus 12. So the system has a unique solution. And now we'll determine the matrices A1. So here we replace the first column of matrix A with the entries in B. So what we have is the second and third columns remaining the same, and we replace the first column with 2, 5, 3. And we'll do the same for matrix A2. So this time the first and third columns remain the same, and we replace the second column of A with the entries in B. And finally, for A3, because we have 3 unknowns, we have the first columns remaining the same, and the final column replaced with the entries in B. And now you can calculate the determinant of A1 using the same method we followed for A. So you'd get 3. And the determinant of A2 can be obtained in a similar way, which will give you minus 27. And the determinant of A3 is 9. So have a go at verifying this yourself. And therefore x1 is the determinant of A1 on the determinant of A, which is minus a quarter, and x2 is the determinant of A2 on the determinant of A, so that would give 9 on 4. And x3 is 9 on the determinant of A, which gives minus 3/4. And you can verify this by substituting these into our system of linear equations to verify the left-hand side is equal to the right-hand side. Vectors are represented as arrows in 2 space, which you probably recognize as 2-dimensional space, or 3 space being 3D. So these arrows have some initial and some terminal point. So we can denote the vector as a letter with an arrow on top, or the vector from a point P to the point Q as follows. So vectors have a length or a magnitude and a direction, unlike scalars or numbers, which only have a magnitude. Now 2 vectors are equivalent if they have the same length and same direction. So as we can see, A is equivalent to B, but these vectors are not equivalent to C. So even if C had the same length as these vectors, it would still have a different direction. And a special vector, being the 0 vector, is a special vector that has the same initial and terminal point. We can add vectors using the head-to-tail method or the parallelogram method. So with the parallelogram method, when adding vectors A and B, we place their tails together and we construct the parallelogram from these vectors. So this line is parallel to vector A, and this line is parallel to vector B. And the resulting vector is drawn from the initial point of both vectors as the diagonal to the opposite end of the parallelogram. So that's our resulting vector C. So our resulting vector C is A plus B. And using the head-to-tail method, we can put the tail, or initial point of B, at the head or terminal point of A. And the resulting vector is drawn from the tail or initial point of A to the terminal point of B. So in this case, we have C is A plus B, And alternatively, we can place the initial point of A at the terminal point of B, and our resulting vector C is drawn from the initial point of B to the terminal point of A. So in this case we have C is B plus A. So as we can see in both cases, we have the same resulting vector C. So therefore vector addition is commutative. We can extend the head to tail method to add more than two vectors. So here we have A plus B plus C. So we can place the initial point of B at the terminal point of A, and the initial point of vector C at the terminal point of vector B. And therefore the resultant vector is drawn from the initial point of A to the terminal point of C. Now we can visualize this better by adding A and B first, using the head to tail method. And then adding this to C using the head to tail method again. So as we can see, our resultant vector is drawn from the initial point of A plus B to the terminal point of C. Now alternatively, we can add B and C first using the head to tail method, and then add A to this result, which gives the same resultant vector. So as we can see, vector addition is also associative. We can visualize vectors when we add them in 3D space or 3 space. So using the associative property of vector addition, we can add A and B first using the parallelogram method, and then we can add this result to C. So again, using the parallelogram method, our resultant vector would look like this. Now alternatively, we could have put the initial point of C at the terminal point of A plus B, so it would look like this. And our resultant vector is drawn from the initial point of A plus B to the terminal point of C. So that gives the same result. Scalar multiplication, or the multiplication of a scalar or number with a vector, basically scales that vector. So here we have a positive scalar between 0 and 1. So effectively multiplying this with a vector is going to make it shorter. And if the scalar was greater than 1, then this vector would be longer, as you can imagine. But it still has the same direction. Now if we have a scalar of -1 multiplied by our vector, well, that just reverses the direction of our vector. And if we have 0 multiplied by our vector, that gives the 0 vector. We can take advantage of vector addition to subtract vectors. So if we want to subtract B from A, for example, then we can first negate B, as we've shown here, which reverses its direction, and then we can add this to A. So using the head to tail method, we place the initial point of minus B at the terminal point of A, which looks like this, and then we draw our resultant vector D from the initial point of A to the terminal point of B, using the head to tail method. So as we can see, this is not the same as B minus A. So in this case, we negated A, and added this to B. So the initial point of minus A is placed at the terminal point of B, and our resultant vector is drawn from the initial point of B to the terminal point of minus A. So these do not give the same vector, and therefore vector subtraction is not commutative. Vectors can be conveniently represented in coordinate systems. So for example, in 2 space or 2-dimensional space, the vector A has components A1 and A2, which in this case signifies the x and y direction. Now in 3 space or 3-dimensional space, noting that there are also different coordinate systems in 2 space, such as polar coordinates, which are extended to 3 space as cylindrical and spherical polar coordinates. We'll generally visualize the vectors in 3 space using Cartesian coordinates. So here the vector would have components A1, A2, and A3 to represent the x, y, and z directions. And in 2 space, the 0 vector has the following components, and in 3 space, it has the following components. And 2 vectors, A and B, are equivalent if all their components are equal. So A1 is equal to B1, A2 is equal to B2, and A3 is equal to B3. And as we've seen previously, we can write A in matrix form. So in 3 space, we can represent it as a column vector or a column matrix, or also a row vector or row matrix. If we have a vector in 2 space, for example, where its tail is not at the origin, so suppose its initial point is at point P and its terminal point is at another point Q. Well, we can use special types of vectors that have the initial point at the origin. So these are called position vectors. So I'm going to call this vector 0 to P. And I'm going to call this second position vector drawn to the terminal point of Q as 0 to Q. So using the vector head to tail method, 0Q is equal to 0P plus A. So therefore the vector A is 0Q minus 0P. Now if we suppose vector 0Q has the components x2 and y2, and 0P has the following components x1 and y1, so therefore the components of vector A can be obtained as x2 minus x1 and y2 minus y1. And if you extend this to 3 space, you'll see that vector A has an additional component in the z direction. Let's extend our ideas of vectors in 2 space or 2D space and 3 space or 3D space to vectors in n space or an n-dimensional space. So you're familiar with R being the set of all real numbers viewed as the real line, and R2 is the set of all ordered pairs, or two tuples, which are points in the plane in 2 dimensions. And R3 also had a geometric interpretation, which are the set of ordered triples, or 3 tuples, which were visualized in 3D space. So extending this idea to Rn, or n space, then a set of all ordered n tuples being a sequence of real numbers. So we have A1, A2 to AN. And for example, our sequence of numbers in 2 space is A1, A2. Now the operations of vectors in Rn extend the vector operations in 2 space and 3 space. Now if we denote the vector A having the components A1 to AN, then in n space the 0 vector has the same number of components, but all zeros. And similar to 2 space and 3 space, we have 2 vectors A and B being equivalent if and only if their components are all equal. So A1 is B1, A2 equals B2, and this continues up to n components. Now we can add vectors in 2 space by adding the individual components. So we have A1 plus B1 and A2 plus B2 being the components of the resultant vector. So you can visualize this by projecting the vector onto the horizontal axes. So A has the component A1 and B has the horizontal component B1. So by geometry, you can see that this distance, A1, is the same as this distance. So adding A1 to B1 gives the component of the resultant vector. And similarly in the vertical direction, we have the vertical component of A and the vertical component of B, and this vertical component of B is the same as this vertical distance over here. So adding A2 and B2 gives the second component of the resultant vector. And similarly in 2 space, we can visualize that the multiplication of a scalar by A is the same as multiplying that scalar by the vector's individual components. And this extends to the subtraction of 2 vectors, where we add A to the negated vector B. So that's the same thing as subtracting their components in the horizontal and vertical directions. So we can generalize these operations to n space while extending the properties of the operations, including linearity, commutativity, and associativity. So we'll extend the operations intuitively to n space, but we won't prove them. So recall that adding A and B is the same as adding B and A. So that's the commutative property. And then adding A and B and adding a vector c to this result is the same as adding a to b and c. So that's the associative property. And we've shown these geometrically using the parallelogram and head-to-tail methods in 2 space. So they're not obvious in n space, but they've been proven. And as you can imagine, adding a vector to the 0 vector gives that same vector. So that's one of the identity properties. And if we multiply a scalar by the sum of 2 vectors, we can distribute the scalar in the parentheses. So we have s by the vector a plus s by the vector b. And similarly, if we add 2 scalars and multiply the result by a vector, then we can distribute the vector inside the parentheses. So we have the scalar s by a plus the scalar t by the vector a. And similarly, the associative property of scalar multiplication can be seen when we multiply a scalar by the result of another scalar multiplied by a vector. So that's the same thing as multiplying the 2 scalars first and multiplying the result by the vector. And we have another identity property, so we have the scalar 1 multiplied by a vector gives that same vector, and the vector a plus the negated vector a gives the 0 vector. And similar to 2 space and 3 space, we can express a vector in n space using the column matrix of its components. So v1, v2 up to vn. And you can also express this vector as a row matrix. So that will be v is equal to v1, v2, and so on up to vn. Let's use the properties of vector operations to solve for the vector x given the following equation. So what we can do is add the negated vector a to both sides, noting we use the commutative property. And using the commutativity of vector addition, minus a plus a is the same as a plus minus a, which is 0. And then we have minus k multiplied by x is equal to b plus minus a, which is the same thing as b minus a. And some vector plus a 0 vector is this vector. So the 0 vector disappears. And now you can do some simple algebra by multiplying both sides by minus 1 on k. Assuming k is not equal to 0. So remember that a scalar multiplied by another scalar and a vector is the same thing as multiplying the 2 scalars and then the vector. So what we get is minus 1 on k by minus k is 1 multiplied by x, and that's equal to minus 1 on k by b minus a. And by the identity property, 1 by x is just x. So therefore, our final result can be presented in the following form. And you can choose to distribute the scalar inside the parenthesis to expand this. So you can see the analogies with algebra performed on the real numbers. The norm, or length of a vector, is defined as follows. So in 2 space, if we consider a vector A, the norm or length of this vector can be obtained using Pythagoras' theorem. So that will be the square root of the horizontal component squared plus the vertical component squared. And similarly in 3 space, which is the case over here, the norm of the vector is the square root of the sum of the squares of its components. So we can visualize this as the length of vector A from point P to Q squared is equal to the square of the length of vector PS plus the square of the length of the vector from point S to Q. And we can obtain the square of the length of the vector PS by applying Pythagoras' theorem again. So that will be equal to the square of the length of vector PR plus the square of the length of vector RS. So effectively we're adding the square of the length of the components of our vector A. So therefore we can generalize this to n space. So we have the norm of the vector is equal to the square root of the first component squared plus the length of the second component squared, and so on up to the nth component squared. So while we won't prove this here, but the norm has been proven for n tuples, we'll base this on 3 intuitive ideas. That distances are non-negative. So this implies the norm of vector A is greater than or equal to 0, and only the 0 vector has a length of 0. So in general, all the vectors have a non-zero length except the 0 vector. And the third idea is that taking the norm of some scalar multiplied by a vector is the same as taking the absolute value of the scalar and multiplying it by the length of the vector. So using this rule over here, we can expand this to the square root of s by a1 squared plus s by the second component squared, and so on up to s by the nth component squared. So note that when we multiply a scalar by a vector, we're multiplying each component by that scalar. And given the scalar can be negative, we take its absolute value outside the square root, which gives the following result. And a special case that has a length of 1 is the unit vector. So the components of this unit vector can be obtained by multiplying the vector by a scalar being the reciprocal of the norm of this vector. And note that this applies for the non-zero vector. So the norm of this vector must be greater than 0. There are special types of unit vectors being the standard unit vectors. So in 2 space, we denote these vectors I hat with a non-zero component in the horizontal direction, and j has a non-zero component in the vertical direction. And similarly in 3 space, we write I hat as having a component of 1 in the horizontal direction, and similarly j has a non-zero component in the vertical direction, and k has a non-zero component in the z direction. So it's normal to the xy plane. And in general, we can express any vector in 2 space and 3 space as a linear combination of these standard unit vectors. So for example, the vector A is the component A1 by the unit vector I plus A2 by the unit vector j plus A3 by the unit vector k in 3 space. So we can generalize these ideas to n space. So in this case, we have a unit vector E1 where the first component is not 0 and the remaining components are all 0. And similarly E2 has the second component being non-zero and the remaining components are all 0. And this continues up to En, where we have all 0 components except for the nth component being the last component. And therefore we can express any vector as a linear combination of these standard unit vectors in n space. So we have A1 E1 plus a second component by the second unit vector, and so on up to the nth component by the nth standard unit vector. The dot product is one way of multiplying vectors. So if we take the dot product between a vector A and a vector B, then that's equal to the magnitude or norm of A by the norm of B by the cosine of the angle between the vectors. And this angle theta will restrict from 0 to pi. And if either of these vectors are the 0 vector, then the dot product is 0. So note that the dot product is also known as the Euclidean inner product, and it returns a scalar quantity. And you can visualize the dot product as the projection of vector A onto vector B. So this projected vector here is the magnitude of A cosine theta, which we can see using trigonometry. So given this restriction of theta, so for example, if we had vector B as follows, and vector A as follows, then we take this as the angle between them. The dot product has several useful properties, and one of those is that it evaluates to 0 when the angle between the vectors is pi on 2. And this can be seen from this cosine theta term. And if the dot product is less than 0, then the angle between the vectors is obtuse. And if the dot product is greater than 0, then the angle between the vectors is acute. And we can see the commutativity of the dot product by the expression on the right hand side. So taking the dot product of B with A is the same as the dot product between A and B. So in this case, it can be seen as the projection of B onto A. So we have the magnitude of B cosine theta in this case, where this is our right angle. We can also evaluate the dot product in component form. So in 3 space, if A has the following components, which are the components in the x, y, and z direction, and B also has similar components, so B1 to B3, then we can evaluate the dot product between A and B by summing the product of each of the components together. So we have A1 B1 plus A2 B2 plus A3 B3. So to see why this works, we can apply the law of cosines. So if we see these vectors arranged in a plane, then the squared magnitude of vector C is equal to the squared magnitude of A plus the squared norm of B. So that gives the squared distance of each edge of that triangle, and minus 2 by the magnitude of A by the magnitude of B cosine theta, being the angle between the vectors A and B. So this here is the law of cosines from trigonometry. We recognize that this here is the dot product between A and B. So if we take this to the other side and take C to the other side and then divide by 2, we get 1/2 by the norm of A squared plus the norm of B squared minus the norm of C squared. And using vector addition, we can see geometrically that vector C is the sum of vector A plus vector B negated. So you can visualize this using the head to tail method and the commutativity of vector addition. So therefore, we can replace the norm of C as the norm of vector A minus vector B. And therefore vector A minus vector B has the components A1 minus B1, A2 minus B2, and A3 minus B3. So if you note that the squared magnitude of A is A1 squared plus A2 squared plus A3 squared, and you'll have a similar expression for B and a similar expression for A minus B. So you're basically just squaring each component and adding them together. So if you substitute those components into this equation and simplify the result, you'll find that the dot product evaluates to the sum of the products of the components of vectors A and B. So I'll leave that for you to do as an exercise. Now that we've seen that the dot product between two vectors is the sum of the products of each of their components. So this is what we had in 3 space. Then we can extend the dot product to n space. So consider a vector A in n space having the components A1, A2 to AN, and another vector B having similar components. So we have B1, B2 to Bn. Then using the component form of the dot product, we can write it in n space as A1, B1 plus A2, B2 up to AN, Bn. So note that due to the analogies between vector spaces and Euclidean geometry, the dot product is also referred to as the Euclidean inner product. The dot product, being the product of two vectors, has similar algebraic properties as the products of real numbers. So recall that the dot product between a vector and itself is the sum of the squares of its components so in n space we have up to the nth component squared. So on the right hand side we have the squared magnitude of A. So if you take the square root of both sides, you get the norm of A is equal to the square root of the dot product of the vector with itself. And the dot product of a vector A with a vector B is the same as taking a dot product between vector B and A, as we saw in 2 space. So that's the commutative property of the dot product. And the dot product is also distributive. So if we take the dot product between A and another vector B plus C, then we can distribute A. So we have A dot B plus A dot C. And note that due to the commutativity of the dot product, this is the same as B plus C dot A, which can also be distributed as B dot A plus C dot A. So due to commutativity, we see that this right hand side is the same as this right hand side. And if we have a scalar multiplied by the dot product between two vectors, then we can multiply the scalar by vector A and then take the dot product. And due to the commutativity of the dot product, this is the same as the scalar by B dot A. So we can write this as S multiplied by B dot A, which is the same as A dot SB due to the commutativity of the dot product. Now the dot product between a vector and itself, as we saw, is greater than or equal to 0. And A dot A is equal to 0 if and only if the vector A is the 0 vector. And as you'd expect, the dot product between a 0 vector and another vector is 0, because the 0 vector has all 0 components. Recall that the dot product between two vectors is equal to the magnitude of A by the magnitude or norm of B, cosine of the angle between them. So we can rewrite the angle as the arc cosine of the dot product over the product of the magnitudes of both vectors. So if we want to extend this to n space, arc cos is not defined unless this expression is between -1 and 1. Now the Cauchy-Schwarz inequality allows us to show that this is true. So this inequality states that the absolute value of the dot product between A and B is less than or equal to the product of the magnitudes of both vectors. And we won't prove this here. So therefore, if we divide through by this expression on the right hand side, then the inequality becomes the absolute value of the dot product over the product of the magnitudes of the vectors is less than or equal to 1, which is basically saying the same thing as this expression. So therefore, given this expression is between -1 and 1, then the angle theta is defined in n space. We can visualize the triangle inequality in 2 space and 3 space, which states that the sum of the two lengths of two sides of a triangle is larger than or equal to the third side. So using vector addition, we have the length of the third side is the magnitude of A plus B. So you can also visualize this as the distance between points. So typically the triangle inequality is written backwards. So we have the magnitude of A plus B is less than or equal to the magnitude of A plus the magnitude of B. So we can see that when A and B get closer to this vector, then the sum of their lengths is always larger than or equal to the length of this vector. And we have a similar expression for the distance between points. So we have the distance between the points P and R. So we connect those with a line. Is less than or equal to the distance between points P and Q plus the distance between points Q and R. So this is basically saying that the shortest distance between 2 points is a straight line. Given that we can represent vectors in matrix form, so in n space, if we have A with the following components, and a vector B has the following components, so this column vector has n rows by 1 column, and this vector has n rows by 1 column. And a product between two matrices is defined if the number of columns in A is equal to the number of rows in B. So therefore, if we want to multiply these two vectors together, we transpose B. Or alternatively, we can transpose A and multiply this by B. And you'll notice that this here is the same as taking a dot product. So for example, if we visualize the transpose of B, it'll look like this. So multiplying these two matrices is the same as taking the sum of the products of the components of the vectors. So for example, this gives A1 B1 plus A2 B2 and so on up to AN BN. So this is exactly the same as taking a dot product between A and B. And this leads to some useful operations. So for example, if we had a matrix multiplied by A dot B, then it's the same as multiplying the transpose of B by the vector that results from multiplying M with A. And then using the associativity property of matrix multiplication, we can write the transpose of B multiplied by M multiplied by A. And furthermore, this is the same as multiplying the transpose of M by B and taking a transpose of this result. And that's multiplied by A. And also note that we can also take the transpose of B and multiply that with A, which is also the same as the dot product between the two vectors, given that we're still multiplying the components. So therefore, the transpose of a vector multiplied by another vector is the same as taking a dot product between that vector and the other vector. We've seen from the definition of the dot product between two vectors A and B, which is equal to the product of the norms of both vectors by the cosine of the angle between them. So therefore, when the angle between the vectors is pi on 2, then the dot product evaluates to 0. So in other words, two vectors are orthogonal if and only if their dot product is 0. And if we have a set of vectors, so for example A, B and C, then this is called an orthogonal set of vectors if all pairs of distinct vectors in the set are orthogonal. So in other words, A dot B must be 0. So we need to check all pairs. So A dot C must also be equal to 0. And B dot C must also be equal to 0 for this to be an orthogonal set. And note that we don't need to check B dot A or C dot A or C dot B because we know the dot product is commutative. And if this was a set of unit vectors, so for example I, J and K, being the direction vectors, of the coordinate axes in 3 space, then if all pairs of vectors are orthogonal, which is the case, then this is called an orthonormal set. So you can verify this by writing out the components of the unit vectors. So for example, I is 1, 0, 0, j hat is 0, 1, 0, and k hat is 0, 0, 1. So taking the dot product in component form, you'll see that I dot j is 0, I dot k is also 0, and j dot k is also 0. Let's observe how orthogonality can be seen in geometry. So if we take the dot product of some normal vector, which is perpendicular to the direction of a line and perpendicular to a plane, so we have the dot product between a normal vector and a vector on a line from P0 to P is equal to 0. And similarly, this equation applies to the dot product between n and a vector on the plane. So in 2 space, we have a line where the components of n are a and b, and the point P0 has coordinates x0 and y0. And in 3 space, we have a plane where the normal vector has 3 components a, b, c, and the point on the plane is x0, y0, z0. So effectively, we can write point normal equations to represent the line and the plane. So for the line in 2 space, if the components of the normal are not both 0, and similar to point P0, the point P has coordinates x, y, then using this equation, the dot product of n with the vector from P0 to P is a multiplied by x minus x0 plus b by y minus y0, and that's equal to 0. So this is the point normal equation of a line. And similarly, we can have a point normal equation for a plane by using this same equation. So we have a by the x coordinate of point P minus that of point P0 on the plane, plus a second normal component by y minus y0, and then plus the third component of the normal vector by z minus z0, and that's equal to 0. So therefore, we can write this equation of a line as ax plus by, and then plus minus ax0 minus by0 is equal to 0. So if we designate this expression as c, then we can write the equation of the line as ax plus by plus c is 0. And similarly for the plane, if we designate D as minus ax naught, minus by naught, minus cz naught, then we can write the equation of the plane as ax plus by plus cz plus d is equal to 0. So for a line through the origin, c is equal to 0. And for a plane through the origin, d is equal to 0. We can represent a vector as the sum of a parallel component, which is the projection of that vector onto another vector, plus the sum of a perpendicular component. And we can visualize this sum using the parallelogram rule. So using trigonometry, we can write the parallel component as the norm of A by the cosine of the angle between A and B. And this component points in the direction of B. So we take the normal vector of B to specify the direction. Now recall the dot product between two vectors was the norm of A by the norm of B by cosine theta. So therefore, if we divide through by the norm of B, then we can rewrite this as A dot B on the norm of B. And this unit vector can be written as the vector B normalized by its magnitude. So therefore, we have A dot B on the squared magnitude of B multiplied by the vector B. And this is the projection of A onto B. Now we can find the perpendicular component by subtracting the projected component from the vector. So we can write A perpendicular as A minus the projected component in the direction of B. So therefore, if we replace this with our expression here, so I'll just copy that across, then that gives this component, which is perpendicular to the projected component. Recall when we took the dot product between two vectors A and B, that returned a scalar. And here we'll define a cross product between two vectors, which results in a vector that's perpendicular to both vectors. And to define this, we'll write the components of vectors A and B in a matrix so noting that the cross product between two vectors is only defined in 3 space, we can obtain the components of the cross product between both vectors by removing one of these columns and taking the determinant of the remaining matrix. So for example, to get the first component of the cross product, we'll remove column 1 and take the determinant of the resulting matrix in column 2 and 3. So we have A2, A3, B2, B3 being the entries of that matrix. And to get the second component, we take the negative of the determinant of the matrix that results when we remove column 2. So that will be A1, A3, B1, B3. And similarly, to get the third component, we remove column 3 and take the determinant of the matrix with entries A1, A2 and B1, B2. So if we expand this, we get the definition of the cross product between two vectors in component form. So remember that getting the determinant of a 2 by 2 matrix includes multiplying the cross terms and subtracting the result. So we get A2, B3 minus A3, B2, and the second component is the negative of the determinant. So that will be A1, B3 minus A3, B1. And the third component is A1, B2 minus A2, B1. Now the fact that the vectors A and B are both perpendicular to the cross product between the vectors can be shown by taking the dot product of A with A cross B and verifying it's equal to 0. And similarly, taking a dot product between B and A cross B will also give 0. So for example, you can verify this result by multiplying A1 with the first component, A2 with the second component, and A3 with the third component, and summing the result, which will give you 0. So I'll leave that for you to do as an exercise, and you can verify the second result in a similar way. And similarly, you can verify Lagrange's identity, which is the squared norm of the cross product between two vectors is equal to the norm of A squared by the norm of B squared minus the dot product between A and B squared. So this here is Lagrange's identity, which will be useful to make some geometric interpretations of the cross product. Using the right-hand rule, we can determine the direction of the vector that results from the cross product between two vectors. So if you take the bottom of your right hand and put it in the plane of vectors A and B, and then curl your fingers from A to B, then your thumb will point in the direction of the resulting vector. And as we've shown previously, this vector is perpendicular to both vectors A and B. And furthermore, if we construct a right-angled triangle between A and B, and designate this angle here between both vectors as theta, then this height over here is the magnitude of B sine theta, and then multiplying this by the magnitude of A gives the area of the parallelogram between both vectors. So we have the base of the parallelogram by the altitude or height. So if we use Lagrange's identity by taking the squared norm of the cross product between A and B, which is equal to the product of the squared norms of both vectors minus the dot product between both vectors squared. And we know the dot product is the magnitude of A by the magnitude of B cosine theta, and we took theta between 0 and pi. So if we substitute for the dot product and factor out the product of the squared magnitudes of both vectors, so we have the squared magnitude of A by the squared magnitude of B by 1 minus cosine squared theta. So using trig identities, this is sine squared theta, and because theta is between 0 and pi, sine theta will always be greater than 0, so therefore we can write the magnitude or norm of A cross B to be equal to the norm of A by the norm of B sine theta, which is the area inside that parallelogram. We can observe some properties of the cross product, and one of those is the cross product between two vectors is not commutative. So it's equal to the negative of taking a cross product of B with A. So one way we can observe this is using the right hand rule. So curling your fingers from A to B, your thumb points in the positive Z direction. Otherwise, if you flip your right hand upside down and then curl your fingers from B to A, you'll get the following vector pointing in this direction, but having the same magnitude as A cross B. Now the cross product is also distributive over addition, so if we have the cross product between a vector A and a vector that results from adding two vectors B and C, then that's equal to the cross product of A and B plus the cross product of A and C. And similarly, taking a scalar multiplied by the cross product between two vectors is equal to the scalar by A crossed with B. And that's equal to the cross product between A and the vector S by B. And intuitively, you can see that the cross product between A and a 0 vector is equal to the cross product between a 0 vector and A, which is the 0 vector. And the cross product between a vector and itself is also equal to the 0 vector. So recall that the magnitude of the cross product is equal to the product of the norms of both vectors by sine of the angle between them. And we showed that that gives the area of the parallelogram formed by those vectors. And the altitude of the parallelogram was B sine theta. So the parallelogram formed between a vector and itself has an area of 0. And using the right hand rule, we can visualize the cross products between the unit vectors. So I cross j is positive k, and I cross k will be minus j. So if you curl the fingers of your right hand from k to I, then your thumb will point in a positive y direction. So taking the cross product in reverse gives a vector that points in the opposite direction. And similarly, j cross k will give positive I. And as you can imagine, the cross product between each unit vector and itself is 0. So you can visualize this using the properties of the cross product. Recall the cross product between two vectors can be evaluated by putting these vectors in a matrix. So vector B goes in a row and vector C goes in a row. And to get the first component, we omit the first column and take the determinant of the matrix in column 2 and 3, and so on. So therefore the components of the resulting vector was B2C3 minus B3C2, and then we had minus B1C3 minus B3C1, and then the third component we have B1C2 minus B2C1. So have a go at verifying this yourself. Now if we take the dot product of this cross product with another vector, then we put this vector in row 1 of this matrix, and then to get the first component, we omit column 1 and row 1 and multiply A1 by the determinant of this minor matrix. And similarly, to obtain a second component, we omit column 2 and row 1 and then multiply A2 by the determinant of the matrix with the following entries that are not in row 1 or column 2. And then in a similar way, we can get the third component by multiplying A3 by the determinant of the matrix with the following components, which is not in column 3 or row 1. And it follows that this triple product is equal to B dot C cross A. So we'll just go on to the right and taking a dot product, then a cross product in this order. So therefore this result is equal to C dot A cross B. So we're always going this way to take the dot product and cross product in order. So if we look at the determinant, what we're doing is two row interchanges. So basically interchanging B with A, and then interchanging A, which is now in the second row, with C. And similarly here, we're interchanging C with A. So now A is in the third row, and then we're interchanging A from the third row with B. So two row interchanges negates the determinant twice. So have a go at verifying this. The determinant of the matrix formed between two vectors with the components a1, a2 in the first row and the components of the second vector in the second row gives the area of a parallelogram in 2 space. And note that given the cross product only applies to 3 space, we give a vector A an additional component of 0 and also the vector B a component of 0 in a direction out of the plane. So therefore the components of A cross B are 0 in the horizontal direction, 0 in the vertical direction, because the resulting vector should be perpendicular to both vectors A and B. And in the Z direction we have A1, B2 minus A2, B1, as we've seen previously by evaluating the determinant. So therefore the magnitude of A cross B is the absolute value of the determinant of the matrix formed by the components of A and B. So therefore the absolute value of the determinant is equal to the area of the parallelogram between A and B. Now in 3 space, the determinant of the matrix formed by the vectors A, B, and C with their components in each row of that matrix. So this is in 3 space. Is equal to the volume of the parallelepiped formed by the 3 vectors A, B, and C. So this can be seen by evaluating the dot product between A and the cross product between B and C. So recall the cross product between B and C is going to give the area of a parallelogram between those vectors. And if we construct a volume between those 3 vectors, they'll look something like this. So we have the face between A and B, and we have a face formed by A and C, and then we can construct the top face using parallel lines to these ones, and the right face by having a line parallel to this one. So this here is called the parallelepiped. So we can see that projecting A onto B gives the following distance, which is the height of the parallelepiped, and then multiplying the base by this height gives the volume of the parallelepiped. So remember that using the projection formula, the height is equal to the absolute value of the dot product between vector A and this vector B cross C on the magnitude of B cross C. So that's the magnitude of the projection of A onto B cross C. And the area of the base of the parallelepiped is the magnitude of B cross C, which is the area of the parallelogram formed by vector B and C. And therefore the volume of the parallelepiped is the base multiplied by the height, which is equal to the scalar triple product. So have a think about this. Today we'll look at real vector spaces. So consider a set V of the following elements. V is called a real vector space with the elements called vectors if the following algebraic operations are defined in V. And these are vector addition and scalar multiplication. And in the context of a vector space, when we refer to vectors, this doesn't necessarily mean the arrows that we're used to that had a magnitude and a direction, but this can refer to arbitrary objects. So in the context of a vector space, these objects can be matrices, functions, infinite sequences, and so on. And when we talk about a real vector space, the scalars used in a multiplication operation are the real numbers, and we can also have a complex vector space, which we'll look at later on, where the scalars will be the complex numbers instead. So the vector addition operation associates with each pair of vectors, being A and B, in the set V, another vector that satisfies the following axioms. And we don't prove axioms. They're basically a starting point for proving theorems. So the first axiom is that the sum of A and B is a unique vector in the set V. So this is called closure under addition. And A plus B is equal to B plus A for any two vectors in V. And you'll recognize this as the commutative property, which you've seen in algebra. And adding two vectors A and B, and then C to the result, is the same as adding A to the result of B plus C for any three vectors in the set V. So this is the associative property. And the zero vector is a unique vector in V, such that for every vector in the set, A plus 0 gives A. And there is a unique vector for every vector in the set V, which is denoted minus A, such that adding minus A to A gives the zero vector. And again, to reiterate, vectors in the context of a vector space are arbitrary objects. Now similarly, scalar multiplication has a set of axioms. So this operation associates with each vector A in V and every scalar S a vector that satisfies the following axioms. So the scalar multiplied by the vector, being the product of S and A, is a unique vector in V. So this is called closure under scalar multiplication. And here we have the distributive property of scalar multiplication. So this applies to every scalar and also every pair of vectors in V. And we have another distributive property where we distribute the vector A over the addition of two scalars. And this applies for every scalar and every vector A in V. And here we have the associativity of scalar multiplication, So multiplying a vector by a scalar, and then multiplying the result by a scalar, is the same as multiplying the two scalars by the vector. And this applies for every scalar and every vector in V. And multiplying one by a vector should give that vector for every vector in V. So if all these axioms are satisfied, then V is called a real vector space, and the elements are called vectors. And while some of these axioms are obvious, we'll look at examples where we'll see that they can actually fail. Let V be the set of all ordered pairs of real numbers with the following addition and scalar multiplication operations on A and B, as shown. And we're asked to determine if V is a vector space. So recall that V is a vector space if it satisfies the following axioms, which I've put here for your reference. And first we'll check closure under addition. So if we have two vectors, for example, A and B, then we can see that adding them together is the same as adding their components. And the result is an ordered pair of real numbers, which is in the set V. So therefore V is closed under addition. And it's straightforward to check the commutative property. So I'll leave that for you to verify that it's satisfied. And the associative property can also be verified quite easily. So if you have a third vector being the following pair, then you can add A and B to C, and then add B and C first and add it to A. And the result will be an ordered pair of real numbers. And similarly, if you add any vector to the zero vector, then you get back that vector. So that'll be also obvious if we look at the zero vector in R2 as having the components 0 and 0. And if you negate any vector and add it to the original vector, you get the zero vector. So this one's also easy to check. Now the scalar multiplication operation is where it gets interesting, because it's not a trivial scalar multiplication. So for the first axiom, we can see that the set V is closed under scalar multiplication, because the result of multiplying a scalar by a vector gives an ordered pair of real numbers. So this ordered pair is in V. And for the distributive property, we basically multiply the scalar by the sum of two vectors. So we just replace A with A plus B. So that will be equal to S by A1 plus B1. And the second component is 0 by this operation. So this is the same as multiplying S with A, which gives SA1 0, and then adding S times B. So that will be S B1 0. And therefore if you add the components together, as per this operation, then these two expressions are equivalent. And I'll let you verify this axiom where we distribute the vector over the addition of two scalars. So you can just write s plus t multiplied by a vector is equal to s plus t by the first component, and the next component is 0. And you can verify that this is equal to the right hand side in a similar way that we did for the previous axiom. And associativity of scalar multiplication can be verified. So s by t by a is the same as s, and then t by a is ta1, and the second component is 0, according to our special multiplication operation. And on the right hand side, we have s by t by a, according to this multiplication operation, is s by t by a1, 0. So we can see that these two expressions are equivalent. Now finally, if we multiply 1 by a, well, according to this operation here, that's the same as multiplying 1 by a1 with the second component being 0. And we know that a has components a1, a2. So these two are not equivalent, meaning 1 by a is not equal to a, and therefore this axiom is not satisfied, and therefore the set of ordered pairs of real numbers, the following operations, is not a vector space, because of this unconventional scalar multiplication. Let V be the set of 2 by 2 matrices with real entries, and the standard matrix addition and scalar multiplication operations. Determine if V is a vector space. Well, in this case, our vector elements are matrices, so we'll write their entries in the usual way we index them. So we have matrix B with similar entries. And you can see that adding A and B results in a 2 by 2 matrix with real entries. So A12 plus B12 and so on. So the set is closed under addition. And we see that adding B and A is the same as adding A and B. And the associative property is also easily satisfied. If we define a matrix C in a similar way and add the components of the matrices together in this order, and this axiom is also satisfied if you consider that the zero matrix has 2 rows and 2 columns of zeros. And this one is also obvious, because if you negate the entries in A and add it to A, we get a matrix of zeros. So I'll leave it for you to do the algebra. And closure under scalar multiplication can be seen if you multiply a scalar by a matrix. So what you get is S multiplied by each entry. So the result is a 2 by 2 matrix with real entries. So therefore the set V is closed under scalar multiplication. And the distributive properties are also trivial to verify, and so is the associative property. So for example, if you multiply this matrix by a scalar t, and then multiply it by s, that's the same as multiplying the two scalars first. So that's straightforward. And similarly, if you multiply the matrix by 1, you're going to get that same matrix. Let V be the set of continuous real-valued functions in the open interval from -infinity to infinity. Determinant B is a vector space given the following operations, being addition and scalar multiplication. So if we visualize this as some vector f having one component and some vector g having another component, now closure under addition follows from this operation. So as we can see, adding f and g of x gives f of x plus g of x, which is an element of V. And closure under scalar multiplication follows from this operation. So if we multiply f by a scalar, that's the same as multiplying the scalar with f of x. So the scalar times f of x is also an element of V. And you should be able to verify commutativity and the associativity of vector addition. And this axiom on the zero vector can be visualized if we plot a function, for example, that's 0 everywhere from -infinity to infinity, and we call this a zero function. So therefore any function plus the zero function gives back that function. And similarly, we can show this axiom is satisfied if we reflect this function about the x-axis. So if you add these two functions anywhere along this interval, the result is a zero function. And similarly, reflecting a straight line, you can always find the negative of the function in the set V, that when summed with the function gives the zero function. So we showed closure under scalar multiplication, and these remaining axioms follow from the properties of real numbers. So have a go at verifying them on your own as an exercise. A subset S of a vector space V is called a subspace of V if S is a vector space under the addition and scalar multiplication operations that are defined on V. So if S is a subspace of a known vector space, then some of the axioms are inherited from the vector space. So we don't need to verify them, such as the commutativity and associativity of the addition operation and the associativity and distributivity of the scalar multiplication operation. So the axioms that are not inherited by the subspace are closure under addition. So for any two vectors in the subspace, then the sum of those vectors must also be in a subspace. And the existence of a zero vector in S is also not inherited from the vector space V. So recall that any vector plus a zero vector must result in that vector, where the vector A is also an element of the subspace. And any vector A in the subspace should have an additive inverse, which when summed with the vector results in a zero vector. And for every scalar S and every vector A in the subspace, the multiplication of the scalar by that vector should also be in the subspace. So these axioms are not inherited by the subspace from the vector space. Now note that these two axioms here follow from the closure under addition and closure under scalar multiplication. So therefore we don't need to verify these axioms either. And therefore S is a subspace of V if and only if it is closed under addition and scalar multiplication. So these are the only two axioms that we need to verify for S to be a subspace of V. Before we look at the subspaces of common vector spaces, let's summarize those common vector spaces in shorthand notation. So first, we call the zero vector space as the set with one element in it, being the zero vector. So we know this is closed under addition and also the scalar multiplication operation of a vector space. So these result in a zero vector which is in this set. Now also the vector space of ordered n tuples or sequence of n real numbers is denoted Rn, and similarly the vector space of infinite sequences is denoted R infinity. And the vector space of matrices with R rows and C columns with real entries is denoted as R by C. And the vector space of real valued functions that are defined at every x in an interval is denoted as F with that interval. So if it's defined at every x from minus infinity to infinity, then we write it as F minus infinity to infinity. And similarly in an open interval, and some closed interval, we denote it as follows. And now let's identify some subspaces of these vector spaces. And remember that the subspace must be closed under addition, and scalar multiplication being the operations of a vector space V. So these are the only axioms we'll have to verify. And also note that every vector space has two subspaces, being itself and its zero subspace. So if we look at the subspaces of the set of ordered pairs of real numbers, well, one of those is the line that passes through the origin. So if we look at two vectors, A and B, lying on that line, then the sum of A and B also lies on that line. So this is inside the subspace, being that line. And similarly, if we multiply a scalar by A, then the resulting vector is also on that line. So therefore, by these two axioms, the line through the origin is a subspace of R2. And by similar reasoning, the line through the origin in 3 space is also a subspace of R3. And also the plane through the origin is another subspace of R3. So if we consider two vectors on this plane, being A and B, then A plus B also lies in that plane. And similarly, multiplying A by a scalar gives the resulting vector that also lies in that plane. And now let's look at some subspaces of the vector space of real valued functions that are defined at every x over the interval from -infinity to infinity. So these can be any functions, and they may not be continuous. So one function may look like this, but is defined at every x in that interval. And recall from calculus that the sum of continuous functions, so we have CA plus another continuous function and a constant multiplied by a continuous function, is also continuous. So therefore, because these result in a continuous function, the set of continuous functions is closed under addition and scalar multiplication. So a continuous function may look something like this. So you draw it without lifting your pen. So therefore, because this subset of the real valued functions is closed under addition and also scalar multiplication, then it's also a subspace of F. And similarly, we'll denote the set of continuous functions with nth order derivatives as follows. In some interval. So similarly from calculus, the sum of continuously differentiable functions. So for example, if the function is differentiable once, we'll put a 1 here. And a constant multiplied by a continuously differentiable function is also continuously differentiable. So therefore C1 is also a subspace of the vector space of real valued functions f. So note that f includes discontinuous functions and continuous functions. And noting that a symmetric matrix, which has to be a square matrix, which we can also denote as follows. If it has real entries, the set of symmetric matrices having the same number of rows and columns is a subspace of the vector space of square matrices. So remember, when we add two symmetric matrices, such as for example the following symmetric matrix, where the off-diagonal elements are the same, with the following symmetric matrix, then you can see the result is also a symmetric matrix. And similarly, if you multiply a symmetric matrix by a scalar, then that also results in a symmetric matrix. So therefore the set of symmetric matrices is a subspace of the vector space of square matrices. And now if we consider a polynomial with a degree of n, recall we can write this as some constant plus another constant by x plus another constant by x squared up to Cn by x to the n. So this polynomial has a degree n. And a set of all polynomials, with the constants being real numbers, is a subspace of the vector space of real valued functions over the interval from -infinity to infinity. And we'll denote this set of all polynomials as p infinity. So when you add two polynomials, no matter what their degree is, so for example p1x plus p3 of x, then the result is a polynomial. And if you multiply a scalar by a polynomial, then that also results in a polynomial. So therefore the set of all polynomials is a subspace of the vector space of real valued functions that are defined at every x in a given interval. And similarly, the set of all polynomials with a degree that's less than or equal to the degree of the polynomial with the highest power, which will denote Pn, is also a subspace of this vector space. As you can imagine, adding a polynomial with degree n or less, so for example a polynomial with degree 1 to a polynomial with degree n, where n is 2, then that's going to result in a polynomial with a degree of 2 or less. So specifically, if we had 1 plus 2x plus 2x squared, and then 1 plus 2x minus 2x squared, so if we add these together, these will cancel, and the result is a polynomial with a degree of 1, which is less than or equal to 2. Let's look at subsets of a vector space that are not subspaces. So suppose we have the set of all points x, y in R2 where x is greater than or equal to 0. So that will be this region over here. So if we have 2 points being x1, y1 and x2, y2, so therefore we can see that point 1 plus point 2 results in a point that's in this region. So therefore the resulting point is in this set. And now if we multiply a scalar by 0.1 for example, and if the scalar is -1, then that will result in a point that ends up here at -x1 minus y1. So therefore this set is not closed under scalar multiplication, and therefore it's not a subspace of R2. And another example is the set of all invertible matrices, which is not a subspace of the square matrices. So for example, if we had a matrix A having the following entries, and a matrix B having the following entries, then the sum of A plus B results in 0, 3, 0, 3. So as we can see, having zeros in one of the columns will give a determinant of 0, and therefore the resulting matrix is not invertible. So therefore it's not in the set of all invertible square matrices. And therefore the set of invertible square matrices is not a subspace of the vector space of square matrices. And another example that's not a subspace of the vector space of real valued functions defined at every point in a given interval is the set of polynomials with a specific degree n. So for example, if we had a polynomial with a degree of 3, so we had 1 plus x cubed, and another polynomial which also has a degree of 3, so 1 plus 2x squared minus x cubed, then you can see that adding these polynomials together will result in these terms cancelling, and the resulting polynomial no longer has a degree of 3. So therefore the set of polynomials with a degree n is not a subspace of F. If L is a vector in the vector space V, L is a linear combination of the vectors v1, v2 up to some vector vs if it can be expressed as the sum of the scalar multiples of each vector. So I have some scalar s1 by v1 plus s2 by v2 and so on up to ss by vs. So these scalars are the coefficients of the linear combination, being L. Now suppose we have a subspace of our vector space V, and this subspace is formed from all possible linear combinations, so L1, L2 and so on, of the vectors in a non-empty set S. So this non-empty set has a certain number of vectors used to form all the linear combinations in that subspace. So this subspace is the span of S. Or in other words, the vectors in this non-empty set span that entire subspace. So the span of S is denoted as follows. So we have the span of this set S, or the span of S. And now let's make this more clear by using some examples. So suppose we have a vector in the plane, or 2 space, in this direction, and we want to find the span of the set containing this vector. So recall the span of S is the subspace formed by all possible linear combinations of the vector in this non-empty set. So therefore, we can write some vector as a linear combination of V, and similarly another vector is equal to C2 times V, and so on. So as we can see, when multiplying this vector by a scalar, we're compressing it, stretching it, or negating it. So effectively the resulting vector is always going to end up on the line through the origin. So we say that the span of S containing that vector is a straight line through the origin. And another example is if we want to find the span of the set containing the unit vectors I hat and j hat. So recall the unit vectors in the horizontal direction and the vertical direction in 2 space. And note that any vector in 2 space can be expressed as a linear combination of those unit vectors. So therefore, the span of S is R2. So effectively these 2 vectors span this entire subspace. Now similarly, if we want to find the span of the set comprising all the polynomials being 1x, x squared up to x to the n, then we know that all polynomials in the vector space Pn can be written as some scalar by 1 plus some scalar by x plus another scalar by x squared up to Cn by x to the n. So these vectors span the vector space Pn, being the set of all polynomials with a degree up to n. Suppose we have a non-empty set of vectors, so a1, a2, up to some vector as in a vector space V. Now if the following vector equation, being a linear combination of these vectors, so we have C2A2 and so on up to CSAS is equal to 0. So if this equation has one trivial solution, where the coefficients of those vectors are all 0, then S is a linearly independent set. Otherwise, if this equation has other solutions in addition to the trivial solution, then S is a linearly dependent set. So for example, if we had the set of unit vectors in 3 space, so writing this equation out for our case here, we have the coefficient c1 by I plus c2 by j plus c3 by the unit vector k, and that's equal to 0. So if we expand this in component form, we have c1 by the unit vector I plus c2 by the unit vector j plus c3 by the unit vector k, and that's equal to the 0 vector in 3 space. So as we can see, the only solution to this equation is c1 is 0, c2 is 0, and c3 is also 0. So given we have one trivial solution, then S is a linearly independent set. Now another example is if we have the set of polynomials being x, 1 minus x squared, and 1 plus 3x squared, in P2, being the vector space of polynomials with a degree less than or equal to 2. So if we write this equation, for this case, we have c1 by x plus the coefficient c2 by 1 minus x squared plus the coefficient c3 by 1 plus 3x squared. And you can think of these polynomials as each being a vector with one component. So for example, polynomial 1 would be the vector with the component x. So we set this here equal to 0. And now we can group the terms. So we have minus c2 plus 3c3 multiplied by x squared plus c1 by x plus c2 plus c3. And that's equal to 0. And now equating coefficients, we get one equation being minus c2 plus 3c3 is equal to 0, because there's no x squared terms on the right hand side. And for the second equation, we have c1 is 0, and our third equation is c2 plus c3 is equal to 0. So as we can see, c1 is 0, and if we add the first and third equation, we get c3 is 0, and therefore substituting c3 into one of these equations, we get c2 is 0. So therefore the set S is a linearly independent set, because we only have one trivial solution to our vector equation. Now another way we can look at linear independence is if we suppose that we have a set S of two or more vectors. So for example A1, A2, and so on. So this set is linearly independent if no vector in S can be expressed as a linear combination of the other vectors in S. Now suppose we have two vectors in 2 space. So for example A1 and A2 with their initial points at the origin. Now because they don't lie on the same line, then these vectors are linearly independent. So as you can imagine, we can't express A1, for example, as a linear combination of A2. Because if we multiply A2 by a scalar, then all we can do is change its length or negate it. So A2 will always remain on the same line. And this also applies to 3 space. So if the two vectors with their initial point at the origin don't lie on the same line, then they're linearly independent. Now in 3 space, suppose we have a plane at the origin that looks something like this. And suppose we have two vectors on the plane and one vector outside the plane with their initial points at the origin. So these 3 vectors are linearly independent because they don't lie on the same plane. So suppose this vector is A1, this one is A2, and this one is A3. So if we scale A1 by some constant, it'll be on the same plane. And scaling A2 by another constant keeps it on the same plane. And now if we try to express A3 as a linear combination of vectors A1 and A2, so we have C1A1 plus C2A2, then we can see that this is not possible. Because when we sum these two vectors, then the resulting vector is still on the plane. So therefore A3 cannot be expressed as a linear combination of A1 and A2, and therefore the 3 vectors are linearly independent. And if we consider the set of unit vectors in 3 space, if we had vector k having components 0, 0, 1, and try to express this as a linear combination of I and j, so we have some constant by I plus another coefficient by j. So this equation can't be satisfied because the third component here of I and j is 0. So we can't find values for constants c1 and c2 that'll satisfy this equation. Determine if the following vectors are linearly independent. So we start off with the equation being a constant multiplied by the first vector plus another constant by the second vector plus a third constant by the third vector. And that's equal to the 0 vector. So from this, we have c1 minus c2 plus 4c3. So we're taking the first component of each vector, and that's equal to 0. And our second equation is 3c1 plus 2c2 plus 3c3 is 0. And then we have 4c1 plus 5c2 minus 2c3 is 0. So we can write this as a matrix of coefficients augmented with the 0 vector on the right. So we have coefficients of 1, minus 1 and 4, 3, 2 and 3, and 4, 5, and minus 2. And now we can take the determinant of the matrix of coefficients. So let's call this matrix A. So we take 1 by the determinant of the minor, which is 2 by minus 2, minus 3 by 5, and then minus 1 by 3 by negative 2, minus 3 by 4. And then we have plus 4, 3 by 5, minus 2 by 4. So what we get is minus 19, minus 18, plus 4 by 7 is 28. So that gives minus 9. And therefore, because the determinant is not 0, then we only have one trivial solution to this homogeneous linear system, being c1 is 0, c2 equals 0, and c3 is equal to 0. And therefore these vectors are linearly independent. Suppose we have a set of finite vectors B. So we have A1, A2, up to the vector AN. And this finite set of vectors is in any vector space V. And B is a linearly independent set. And the set B also spans the vector space V. Then B is called a basis for the vector space V. So note that basis vectors aren't necessarily orthogonal unit vectors. So they need to be linearly independent and span V, such that all vectors in the vector space can be expressed as a linear combination of these vectors. And basically, they identify a direction and spacing. And the basis vectors can have different units in different directions. So for example, x can refer to space and y can refer to time. So having the same units and spacing in both directions is important in geometry, but not other applications like physics, where different physical quantities are used. Now let's look at a few examples. So suppose we have a set of finite vectors being the unit vectors in 3 space. Well, as we've shown previously, set B is a linearly independent set. So these unit vectors cannot be expressed as a linear combination of the other unit vectors. And B spans the vector space R3. So therefore B is a basis for V, as it satisfies these conditions. So any vector in 3 space can be expressed as a linear combination of these basis vectors. So in this special case, these vectors form a standard basis for R3. Now suppose we have the set of vectors being 1, x, x squared, up to x to the power of n, in the vector space of polynomials with a degree less than or equal to n. So recall that we can treat these as vectors with one component, and we've shown previously that B forms a linearly independent set. Because recall that the coefficients multiplied by these vectors sum together, so we have C0 plus C1x plus C2x squared, and so on up to Cn by x to the n is equal to 0 only if these coefficients are all 0, which is the trivial solution. Noting that x has an arbitrary value in the interval from -infinity to infinity. And recall that any polynomial with a degree less than or equal to n can be expressed as the linear combination of these polynomials. So therefore, the span of B is the vector space Pn. So effectively B spans this entire vector space. So any polynomial with a degree less than or equal to n can be expressed as a linear combination of these polynomials. So therefore B is a standard basis for Pn. And let's do one more example where we have B being a set of matrices M1, M2, M3 and M4. So M1 has an entry of 1 in the first row and first column, and 0 is otherwise. And similarly, M2 has a 1 in column 2 and 0 otherwise, and M3 has a 1 in row 2 column 1 and 0s otherwise, and M4 has a non-zero entry in row 2 on column 2. And we want to see if this set of matrices forms a basis for the vector space of 2 by 2 matrices. So to show this, we test for linear independence. So we have a coefficient C1 by M1 plus C2 M2 plus C3 M3 plus C4 M4. And we set that equal to 0. So therefore this equation only has the trivial solution, because we have C1 by 1 plus 0 by C2 is 0 plus 0 by C3 plus 0 by C4 is equal to 0. So therefore C1 is equal to 0. And by a similar argument, C2 is equal to 0 and C3 is 0 and C4 is also equal to 0. So therefore B is a linearly independent set. And now we want to verify if B spans its vector space. So therefore we set this equation equal to some arbitrary matrix, so that has arbitrary values of B11, B12, B21 and B22. So now this equation has a solution where C1 is equal to B11, C2 is equal to B12, C3 is equal to B21 and C4 is equal to B22. So given these entries are arbitrary, then B spans its vector space of 2 by 2 matrices. So given these two conditions are satisfied, then B is a standard basis for the vector space of 2 by 2 matrices. Some vector spaces have no basis because they don't have a finite spanning set. And an example is R infinity. So suppose we have a finite spanning set of vectors with an infinite number of components, being 1, 0, 0, and so on with all zeros. And then we have 0, 1, 0 with the rest of the components being 0, and 0, 0, 1 with the rest of the components being zeros, and so on, up to some vector that has all 0 components and a single component of 1. And this has to be a finite spanning set. So we have a finite number of vectors, and therefore this finite set of vectors in R infinity cannot be used to represent every vector in this vector space. So therefore this vector space has no basis, because that is a finite spanning set which can't represent a vector with infinitely many components. And another example is a vector space of polynomials with an infinite number of terms. And suppose we have a finite set of vectors being P0, P1, P2, and so on, up to Pn. So given we have a finite number of polynomials, any polynomial with a degree less than or equal to n can be written as a linear combination of these polynomials. And therefore this vector space has no basis. If a vector space V has a basis, being the finite set of vectors in V, then every vector in V can be expressed in exactly one way, being the linear combination of these basis vectors. So we're up to the scalar Cn by An. And these scalars are called the coordinates of vector A relative to the basis B. So if we can find more than one basis for the given vector space, then we can have different coordinates of A depending on those basis vectors. So we can express this as a coordinate vector relative to the basis B. So that's equal to those coefficients of the linear combination of the basis vectors. So for example, in 3 space, we can visualize this vector as having some x coordinate, some y coordinate, and some z coordinate. So we can write this vector as a linear combination of the basis vectors. And therefore the coordinates of A relative to the standard basis, being the finite set of unit vectors, are x, y, z, which are the coefficients of this linear combination. Let's determine if the following vectors form a basis for R2. So we have some constant by the first vector plus some constant by the other vector is equal to the 0 vector. So we first test for linear independence. So that gives a system of linear equations. So we have C1 plus 3C2 is equal to 0, and 2C1 plus C2 is equal to 0. And therefore our matrix of coefficients is 1, 3, 2, 1. And if we take the determinant of this matrix, we get 1 by 1 minus 3 by 2, which is minus 5. And given that the determinant is non-zero, then this system of equations only has one trivial solution, being C1 is equal to 0 and C2 is equal to 0. So therefore the set of these vectors is a linearly independent set. And now we must test if this finite set of vectors spans this vector space. So to do that, we set the right hand side of this equation to some arbitrary vector. So we have b1, b2 being the components of that vector. So again, given the determinant is not 0, then the inverse exists. So our solution vector can be written in the form of the inverse of this matrix by the vector b. So therefore this system of equations is satisfied for an arbitrary vector b, and therefore b spans R2. So given these two conditions are satisfied, then the finite set of these vectors is a basis for R2. Given that we found in a previous problem that the finite set containing these vectors form a basis for R2, we're asked to find the coordinate vector of this vector with the following components relative to this basis. So therefore this vector with components 4 and minus 5 is equal to some coordinate, being the coefficient, multiplied by the first basis vector plus the other coordinate by the second basis vector. So on the left hand side we have C1 plus 3C2 is equal to 4 on the right hand side, and then 2C1 plus C2 is equal to minus 5. So therefore this is a non-homogeneous linear system that can be solved by taking the inverse of the coefficient matrix and multiplying by the vector on the right hand side. So therefore we can write this as C1 C2 is equal to the inverse of the coefficient matrix by the vector with the following components. So I'll leave it for you to find the inverse, and you'll obtain C1 is minus 3.8 and C2 is 2.6. So therefore we can write the coordinate vector relative to the basis, being the finite set of these vectors, is equal to minus 3.8 and 2.6. And then we're asked to find the vector that has the following coordinate vector relative to this basis. Well, what we do is write the vector as a linear combination of the basis vectors using the components of the coordinate vector. So what we have is 3 by the first basis vector minus 2 by the second basis vector. So for the first component we get 3 minus 6 is negative 3, and then we have 3 by 2 is 6 minus 2 by 1, which is 4. Suppose we have a basis and this is any basis for a finite dimensional vector space V. Then any set with more than n vectors is linearly dependent, as we've seen. And any set with less than n vectors does not span V. Now the dimension of a finite dimensional vector space, which is denoted dim V, is the number of vectors, being n, in a basis for V. Where the dimension of the zero vector space is defined to be 0. So let's look at a few examples. So we'll find the dimension of the vector space Rn. So we know that the basis for this vector space has n vectors. So remember that the standard basis for R2 had 2 vectors, and the standard basis for R3 had 3 vectors. So these effectively have a dimension of 2 and 3. And therefore the dimension of Rn is n, because the standard basis has n vectors. Now the dimension of the vector space of polynomials with a degree less than or equal to n is equal to n plus 1. So remember, the standard basis for Pn had the following vectors, so 1x, x squared, up to x to the n. So we have n plus 1 vectors forming the standard basis. And similarly, the dimension of the vector space of matrices with some number of rows by some number of columns is equal to the rows multiplied by the columns. So if you recall, the vector space of 2 by 2 matrices that we covered had the following standard basis, comprising of the 4 matrices that have a single entry of 1. So this vector space would have a dimension of 4. Suppose the vector space V had a dimension being equal to some number of vectors, and suppose S is a set in V with n vectors. So S is a basis for V if and only if one of the following conditions is satisfied. And the first one is that S spans V. And the second condition is S is linearly independent. So for example, suppose we have a set that has the following vectors, with the components -1, 4 and 3, 3. And we want to determine why this set forms a basis for R2. Well, we know that these vectors can't be expressed as scalar multiples of each other because one of them has a positive and negative component and the other has two positive components. So therefore, given these vectors are linearly independent, and we already know the dimension of R2, which is equal to the number of vectors here, so we can conclude that these vectors form a basis for R2. So we only needed to verify one of these conditions. If S is a subspace of a finite dimensional vector space being V, then the dimension of the subspace must be less than or equal to the dimension of the vector space. So therefore, S is also finite dimensional. And the subspace must be equal to the vector space if and only if their dimensions are equal. So this is quite intuitive. We're asked to find the dimension of and a basis for the solution space of the following homogeneous linear system. And we've solved it some time ago using Gaussian elimination and found the following solution, which we write in parametric form. Therefore, the solution tuple, being the tuple x1, x2, x3, and x4, is equal to some scalar t multiplied by a vector. So here we have x1 is 0, so the first component is 0. x2 is equal to 4t. x3 is minus 5 on 2t. And x4 is equal to t. So our basis consists of one vector with the following components. And as we can see, for an arbitrary solution vector, we can express it as a linear combination of the basis vector. So basically just multiplying this vector by a scalar, and we can obtain any vector in the solution space. So therefore the set comprising this vector spans the solution space of the homogeneous linear system, and therefore the dimension of this solution space is equal to the number of basis vectors, which is 1. So as we can see, we can cover the entire solution space using one vector. Given a basis comprising the vectors b1, b2, up to bn, for a finite dimensional vector space being V, and if the vector VB is the coordinate vector of a vector v relative to this basis, then the mapping from v to vb is a one-to-one mapping between vectors in a general vector space to n space. So in other words, if we write some vector as a linear combination of the basis vectors, then the coordinate vector relative to this basis in matrix form can be written as these coefficients. So in other words, we've mapped the vector v, which is in some general vector space, to another vector, being the coordinate vector, in n space. And this mapping is one-to-one. Some problems are solved more easily using one basis over another. So therefore, it's important to perform a change of basis. So given we have a basis comprising the vectors b1, b2, so we'll start with 2 dimensions, and this can be easily extended to n-dimensional vector spaces. So this is the current basis, and we'll denote b dash as the new basis. So we have b1 dash and b2 dash being the vectors that form this basis. So therefore the coordinate vectors of the new basis being b1 dash and b2 dash and we'll put a subscript b because these coordinate vectors for the new basis are relative to the old basis. So we'll call the components b11 and b21, and the components of b2 dash are b12 and b22. And these are the coordinates of b2 dash relative to the basis b. So therefore, we can write b1 dash as a linear combination of the old basis vectors. So we can write b11 by b1 plus b21 by b2. And similarly for b2 dash, we express it as a linear combination of these vectors using the coordinates. So we have b12 by b1 plus b22 by b2. Now suppose we have an arbitrary vector v that has some coordinates c1 and c2 relative to the basis b dash. Then we express it in terms of the basis vectors b1 dash and b2 dash. And now we want to find the old coordinates of v. being the coordinates relative to the basis b. So what we do is substitute for b1 dash, which gives c1 by b11 by b1 plus b21 by b2, and then we have c2 by b2 dash. So b12 by b1 plus b22 by b2. And now we can group the terms. So we have c1 by b11 plus c2 by b12, and that's multiplied by b1, and then we have c1 by b21 plus c2 by b22 by b2. So we've expressed the vector as a linear combination of the basis vectors in the old basis b. So the coordinate vector of v relative to the basis b can be written in matrix form. So we have this first coordinate, and this is our second coordinate. So we can write b11 and b12, and that's multiplied by c1 and c2. And similarly, in the second row, we have b21 by c1 plus b22 by c2. So verify this using matrix multiplication. And as we said, c1 and c2 are the coordinates of v relative to the new basis. So therefore we can replace this vector with vb dash. So each column of this matrix are the coordinates of the new basis vectors relative to the old basis. So as we can see, b11 and b21 are the coordinates of the new basis vector b1 dash relative to the old basis, and similarly for b2 dash. So this transformation matrix can be used to transform the coordinate vector relative to the new basis b dash to a coordinate vector relative to the old basis b. We saw that we can transform a coordinate vector with the coordinates relative to a new basis b dash into a coordinate vector relative to the old basis b. And we did that by multiplying by a transition matrix. So in this case, our transition matrix for the change of basis from b dash to b had the columns being equal to the components of the coordinate vector relative to the old basis, which were b11, b21, and for the second vector, b2 dash having coordinates relative to the old basis of b12, b22. So remember that this came from expressing these vectors in terms of the vectors that form the old basis. So for example, we had b1 dash is equal to b11 by b1 plus b21 by b2. And the same goes for b2 dash. So we're basically writing the vectors of the new basis as a linear combination of vectors for the old basis. Where the coefficients are the coordinates of the basis vectors for the new basis relative to the old basis. So have a think about this. So more generally, for n basis vectors, we'd have the transition matrix, or the change of basis from b dash to b, being equal to the coordinate vector b1 dash relative to b, and we augment this with b2 dash relative to b, and then keep augmenting vectors until we get to bn dash relative to b. So each column has the coordinates of each basis vector of the new basis relative to the old basis. So therefore, the transformation matrix in the other direction for the change of basis from b to b dash can be written using the coordinates of the old basis vectors relative to the new basis. So we'll just augment these together so they take up each column of the transition matrix. So we keep going until we get to the coordinate vector for the basis vector bn. So these are the coordinates of the old basis vector relative to the new basis. So therefore, to perform a change of basis from b dash to b, we just multiply the transition matrix by the coordinate vector relative to b dash, and that gets transformed into a coordinate vector relative to b. And similarly, if we want to transform a coordinate vector from b being the old basis to the new basis, so we have a coordinate vector for some vector v relative to the old basis, and this gets transformed to another coordinate vector for v relative to the new basis. So note that if we perform the transformation from b dash to b, and then we multiply this by the transition matrix from b to b dash, so basically we're starting from the new basis and performing a change of basis to the old basis b. And then from b, we get back to the new basis. So effectively, we perform the change of basis from B dash back to B dash. So therefore, this is equal to the identity matrix, because basically the net effect of these two operations are going to leave each coordinate vector unchanged. So therefore, if T is the transition matrix from a basis B dash to B for a finite dimensional vector space, then T is invertible, and its inverse is the transition matrix from basis B to B dash. Let's find a systematic way to determine the transition matrices between bases for the vector space of n tuples. So for example, if we had the following vectors forming the standard basis for R2, so we had B2 is 0, 1, and the vectors forming another basis, B dash, have the following components, being 3, 1, and B2 dash has components of 1 and 1. And suppose we want to find the transition matrix to do a change of basis from B to B dash. Well, what we do is write the old basis vectors in terms of the new basis vectors. So what we have is B1 is equal to some coordinate A relative to B dash plus another coordinate B relative to the basis B dash. And similarly, we can write the other old basis vector using another coordinate relative to B dash plus another coordinate D relative to B dash. And now we'll substitute for the components. So we have B1 is 1, 0 is equal to A by B1 dash plus B by B2 dash. And in the second equation, we have B2 is equal to C by B1 dash plus D by B2 dash. So what we have is 3A plus B is equal to 1, and A plus B is equal to 0. And our other set of equations are 3C plus D is equal to 0, and C plus D is equal to 1. And now, given both sets of equations have the same coefficient matrix, being 3, 1, 1, 1, we can solve both of these systems of linear equations simultaneously. So for the first set of equations, we augment 1, 0, and we augment 0, 1 from our second set of equations. And now we can use Gauss-Jordan elimination to reduce this system to a reduced row echelon form. So we subtract minus 1/3 by row 1 from the second row. So let's rewrite the first row. So what we have is 0. 1 minus 1/3 is 2/3. 0 minus 1/3. And 1 minus 0. And we can multiply the second row by 3 on 2 to get a 1 on a diagonal. So minus 1/3 by 3 on 2 is minus a half. And 1 by 3 on 2 is 3 on 2. And now we can subtract row 2 from row 1. So we have 3 minus 0 is 3. 1 minus 1 is 0. 1 minus negative a half is 3 on 2. And 0 minus 3 on 2 is minus 3 on 2. And now we can multiply row 1 by 1/3 to get a 1 on a diagonal. So we have 3 on 2 by 1/3 is 1/2. And minus 3 on 2 by 1/3 is minus a half. So therefore, we end up with our transition matrix from B to B dash, which is 1/2 minus a half, minus a half, and 3 on 2. So to go from the old basis to the new basis, we've started by augmenting the matrix of new basis vectors with the matrix comprising the old basis vectors. So we put each basis vector in a column. So that was our first step. And then we applied Gauss-Jordan elimination to reduce this to our echelon form with the identity matrix on the left and our transition matrix from the old basis to the new basis on the right. So let's just get rid of this line over here. So essentially, if we wanted the transition matrix to go from B dash to B, well, now the old basis is B dash and B is the new basis. So we put the basis vectors B1 and B2 on the left this time, because this is the basis that we want to change to, and the old basis is going to be B dash, which has vectors 3, 1 and 1, 1. So we put each vector in the columns. So now we can see that we already have the identity matrix on the left hand side. So our transition matrix to go from B dash to B is simply 3, 1, 1, 1. And you can verify that this is the inverse of this matrix. So if you multiply them together, you'll get the identity matrix. So given that this is the standard basis, to go from some basis to the standard basis in n space, our transition matrix can be directly obtained by augmenting the vectors of the basis b dash. So generally we have b1 dash, b2 dash, and so on, augmented with bn dash. So we have the basis vectors of b dash in each column of the transition matrix, which we obtain directly, as we showed here, when changing basis from b dash to the standard basis in n space. Given a matrix that has p rows and q columns, recall that we can represent it as a single column of row vectors. So row 1, row 2, up to row p, where the row vectors consist of the components in the respective row. So for example, row p will have the components AP1, AP2, and so on, up to APQ. And similarly, we can represent the matrix using column vectors. So we have C1, C2, up to CQ. So for example, the column vector CQ has the components being the entries in the last column. So we have A1Q, A2Q, and so on, up to APQ. Now the row space of matrix A is the subspace of the vector space of q tuples spanned by these row vectors. So effectively the span of the set of row vectors from R1 to Rp is equal to the vector subspace R, which is a subspace of Rq. And similarly the column space is the subspace of Rp that's spanned by the column vectors of A. So in other words, the span of the set of column vectors being C1, C2 up to column Q is equal to C, and C is a subspace of Rp that's spanned by these column vectors. So note that here we have Rq because each row vector has q components, and here we have Rp because each column vector has p components. So think about this. Now the null space of the matrix A is the solution space of the homogeneous system of equations And the solution space, for example, consists of the solutions x1, x2, and so on. So the solution space of Ax equals 0 is the null space of the matrix A, and the null space is also a subspace of Rq, or the vector space of Q tuples. Because remember that each row vector had Q components, and therefore each solution vector will have the same number of components. Recall that the matrix product, A multiplied by X, can be written as a linear combination of the column vectors. So that would be x1 by the column vector 1 with the following components, plus x2 by c2, and so on, up to xq by the column vector in column Q. So therefore this linear system can be written as Ax is equal to the linear combination of the column vectors, which is equal to the vector B on the right hand side. Then we say that Ax equals B is consistent if and only if B can be expressed as a linear combination of the column vectors of this matrix A. Or in other words, if the vector B is in the column space of A. So what we would do is solve for X by Gaussian elimination, and then express the vector B as a linear combination of the column vectors to show that it's in the column space of A. Recall that if xp is a particular solution of a consistent linear system, Ax equals B, and S being a set of vectors S1, S2 up to SR is a basis for the null space of A, then every solution of Ax equals B can be written as the particular solution plus a linear combination of the basis vectors for the null space of A. So we have C1 by S1 plus C2 by S2 plus another constant CR by SR. So in other words, the general solution of the consistent linear system can be expressed as a superposition of the particular solution of Ax equals B being the non-homogeneous system, and the general solution of Ax equals 0 being the corresponding homogeneous system. So remember in a previous example we had this as matrix A, and this as vector B, and we solved for this system and obtained the following solution. So we used Gaussian elimination with back substitution to do that. And similarly, we also solved for the homogeneous linear system, being AX equals 0, and obtained the following solution. And if you rewrite this in matrix form, so I have x1, x2, x3, x4 is equal to t, being a real parameter, multiplied by 0, 4, minus 5 on 2, and 1. So recall that this here is the basis vector for the null space of A. So here we can see that we have 0, 4t, minus 5 on 2t, and t. So therefore the particular solution, xp, is equal to minus 9 on 2, minus 5 on 2, 15 on 4, and 0. So as you can see, we can superimpose xp plus the linear combination of the basis vectors in the homogeneous solution to obtain a general solution for the consistent linear system AX equals B. We're going to show that elementary row operations do not change the row space and null space of a matrix, but they alter the column space. So given a simple example, if we reduce this to row echelon form by row reduction, we subtract 2 by the first row from the second row. So we have 1, 2, and 0, 0. So now if we want to determine the row space of A, we write some arbitrary vector B with components B1, B2 as a linear combination of the row vectors. So there'll be some constant by 1, 2 plus some other constant by 2, 4. So here we're solving the linear system being C1 plus 2C2 equals B1, and 2C1 plus 4C2 is equal to B2. So we augment the coefficient matrix with the components of the vector B. So in this case, if you subtract 2 by row 1 from the second row, we obtain 0, 0, and B2 minus 2B1. So for this to be consistent, we have B2 minus 2B1 must be equal to 0. Now similarly, we can write an arbitrary vector with components B1, B2 as a linear combination of the row vectors of the reduced matrix. So that'll be 1, 2 plus C2 by 0, 0. So in this case, we have C1 is equal to B1 and 2C1 is equal to B2. So if we multiply the first equation by 2 and subtract the first equation from the second, we can see that B2 minus 2B1 is equal to 0. So effectively, the row vectors in both matrices span the same space. Now if we try this with the column vectors, so we have 1, 2, and 2, 4 being the column vectors of A, you're going to get the same condition. And now using the column vectors of the reduced matrix, we have some vector with components b1, b2 is equal to a scalar by the column vector 1, 0 plus another scalar by the column vector 2, 0. So in this case, we have C1 plus 2C2 is equal to B1, and 0 is equal to B2. So you can see that from this condition, to check for consistency, B2 minus 2B1 is clearly not equal to 0. So therefore the reduced matrix and the matrix A do not have the same column space. And now for the null space, we want to verify that the solution space of AX equals 0 is the same as the solution space of Rx equals 0, being the null space of the matrix A and R. So remember that doing the row reduction, we have 1, 2, 2, 4 augmented with 0 on the right hand side, and here we have 1, 2, 0, 0 augmented with the 0 vector. So this tells us that x1 plus 2x2 is 0, and if you subtract 2 by row 1 from this second row, we get zeros, and this gives us the same result. x1 plus 2x2 is 0. So if we designate x2 as some parameter r, then x1 is minus 2 by r. So therefore we can write the solution as x1, x2 is equal to r by minus 2, 1. So this basis vector spans the solution space, or the null space, of both A and R. So the elementary row operations did not change the null space of the matrix A. If we have a matrix that's already in row echelon form, then the row vectors with leading ones form a basis for the row space of matrix A. So for example, here we have 3 rows with leading ones. So the first row vector is 1, 0, 2, 5, and the second row vector is 0, 1, 2, 1, and the third row vector is 0, 0, 1, and 5 on 2. So these row vectors form a basis for the row space of A. Now alternatively, the column vectors with leading ones of the row vectors form a basis for the column space of the matrix A. So here we have a leading 1 in this row. So the column vector 1, 0, 0, and we have another leading 1 in this row. So we have another column vector 0, 1, 0, and a leading 1 in this row. So we have the third column vector 2, 2, 1. So these three column vectors form a basis for the column space of A. As we saw, doing elementary row operations on A alters the column space. So for example, where B is obtained by subtracting 4 by row 1 from row 2, the row space and null space of both matrices is the same as we showed previously, but the column space is no longer the same. So if A and B are row equivalent matrices, then a given set of column vectors of A are linearly independent. So for example, we can write some scalar by the first column vector in A, which is 1, 4, plus another scalar by the second column vector is equal to the 0 vector. So these vectors are linearly independent if and only if the corresponding column vectors of B are linearly independent. So we must have some constant by the first column vector of B, which is 1, 0, plus another scalar by the second column vector of B being equal to 0, only if C1 and 2 is equal to 0. So remember that a basis means that the column vectors are linearly independent, and any vector in the column space can be written as a linear combination of these column vectors. So this set of column vectors 1, 4, and 2, 8 forms a basis for the column space of A if and only if the corresponding column vectors of B, which are 1, 0, and 2, 0, form a basis for the column space of B. So again, any vector in the column space can be expressed as a linear combination of the column vectors in B. And the column vectors of B must also be linearly independent to form a basis for the column space of B. So what these basically tell us is that the elementary row operations do not affect the relationships between the column vectors in both matrices. So in this case, given that column 2 in A is equal to 2 multiplied by the first column in A, then these columns are linearly dependent, and consequently the columns in B are also linearly dependent. So as we can see, column 2 in B is still equal to 2 multiplied by column 1 in B. And we can see that in B we only have one row with a leading 1, and therefore the corresponding column that forms a basis for the column space of B is the column with the vector 1, 0. And correspondingly, if column 1 in B forms a basis for the column space in B, then column 1 in A is the corresponding column that forms a basis for the column space of A. So effectively, we reduce A to row echelon form, and then we can find a basis for the column space of the reduced matrix formed by some of the column vectors in that matrix, and the corresponding column vector in matrix A forms a basis for the column space of A. Suppose we have a set of vectors being v1, v2, up to some vector vr. And we want to find a subset of these vectors that forms a basis for the span of S. And we want to express the vectors not in that basis, so the other vectors, as a linear combination of the basis vectors. So for example, if we have a set of vectors being 0, 1, 2, 1, 0, 2, two, 2, 4, and 1, 5, 2. So what we will do is assemble these into a matrix of column vectors. And if we reduce this matrix to row echelon form by elementary operations, then we obtain this matrix with the column vectors C1, C2, C3, and C4. And we'll look for the rows with leading ones, which occur in columns 1, 2, and 3. So therefore, the corresponding columns 1, 2, and 3 form a basis for the column space of this reduced matrix R. And therefore the corresponding vectors in columns 1, 2, and 3 of this matrix A, which is row equivalent to R, form a basis for the column space of A. Now to write the remaining column that's not in the basis for the column space of A as a linear combination of the other column vectors forming the basis, then it's simpler to do so with the reduced matrix. So what we can write is column 4 having the components 5, 1 and 5 on 2, being equal to some constant by the first column vector plus another constant by the second column vector, and then plus a third constant by the third column vector. So we can see that C3 must be equal to 5 on 2, because we have 0 plus 0 plus 5 on 2 is 5 on 2. And C2 must be equal to minus 4, because we have 5 on 2 by 2, which is 5, minus 4 by 1 plus 0 is equal to 1. And therefore C1 must be 0, because we have 5 on 2 by 2 is 5, plus 0 by 1 is 5. So therefore the column vector in column 4 is equal to 0 by the column vector in column 1, minus 4 by the column vector 2, plus 5 on 2 by the column vector 3. And consequently, for matrix A, we have the column vector 4 is equal to minus 4 by the column vector 2, plus 5 on 2 by the column vector 3. And I'll leave it for you to verify that this is valid for this matrix. The rank of some matrix A, which has some number of rows by some number of columns, is equal to the common dimension of the row space of A and the column space of A. So remember that when we reduce the matrix to row echelon form, we had the leading ones in each row determining the dimension of the row space, in this case being 3, and that was equal to the same as the dimension of the column space, which is obtained using the corresponding columns to these rows with leading ones. And because the dimension of the row space of the reduced matrix to row echelon form is the same as the dimension of the row space of matrix A, and the dimension of the column space of both matrices is also the same, then you can see why this relationship holds. So therefore, given a dimension of the row space of the reduced matrix is 3, then the rank of this matrix is 3. Now the nullity of matrix A is equal to the dimension of the null space of A. So recall that we wrote the solution vector is equal to some parameter, being a real number, multiplied by the basis vector, which we obtained by row reduction. So therefore in this case, the nullity of our matrix A is equal to the dimension of the null space, which is 1. And we can see that the rank of A plus the nullity of A is equal to the number of columns of the matrix A. So in other words, the rank of the matrix A is equal to the number of leading variables in the general solution for the homogeneous system Ax equals 0, and the nullity of A is equal to the number of free variables, or parameters in a general solution. So here we have one parameter, being t. If we have a consistent non-homogeneous linear system, Ax equals b, and this system has E equations and U unknowns. So for example, by looking at A, we have 3 equations and 4 unknowns. Now if A has some rank, then a general solution of this system contains U minus the rank of A parameters. So remember that when we reduce this system to row echelon form, then for the homogeneous system, the solution space was described by one parameter. So as we can see, the number of unknowns is 4 and the rank is 3, which gives the number of parameters in the general solution of the homogeneous system. But also remember that we can express the non-homogeneous solution as a particular solution plus the general solution to the corresponding homogeneous system, which is this one over here. So therefore the general solution of both systems has this many parameters, being the number of unknowns minus the rank of the coefficient matrix. A system of linear equations being Ax equals b is overdetermined if we have more equations than unknowns to solve for. So suppose this matrix has p rows and q columns, then if the number of rows is greater than the number of columns, then this linear system is inconsistent for at least one vector b in P space, which is the vector space of P tuples. So note that in this case, our system of equations can look something like this. So we have our matrix A, which is a 3 by 2, and by matrix multiplication, that must be multiplied by a 2 by 1 vector. So we have a 3 by 2 by 2 by 1. So remember, the number of columns in A must be equal to the number of rows in X for this to be a valid matrix multiplication. And therefore our resulting vector on the right hand side will be a 3 by 1 vector. So we have the components b1, b2 and b3. Now if we augment our matrix A with our vector b, and if we subtract 2 by row 1 from row 3, we get a 0 and minus 2b1. And if we subtract 2 by row 2 from row 3, then we get a 0 and minus 2b2. So therefore for this system to be consistent, b3 minus 2b1 minus 2b2 must be equal to 0. So therefore at least one vector b is not going to satisfy this condition, which is the consistency condition for our overdetermined system. An underdetermined linear system, ax equals b, has fewer equations than unknowns that we want to solve for. So consider this matrix being a p by q matrix. Then if p is less than q, our linear system is underdetermined. So in this case, for each vector b in the vector space of p tuples, our system here is either consistent or has infinitely many solutions. So for example, given the matrix A on the left hand side, which has the following entries. So this is a 2 by 3 matrix. So our vector x must have 3 components. So a 2 by 3 by a 3 by 1 matrix results in a 2 by 1 vector on the right hand side. So now let's augment this matrix with vector b. So here we can see that the matrix is already in reduced row echelon form. So therefore we can't reduce it further. So if we designate x3 as the free parameter, then our second equation is x2 is equal to b2 minus 2x3, which is t, and x1 is b1 minus 2x3. So now we can write our solution in matrix form. So we have our solution vector. So we have x1 is b1, x2 is b2, and x3 is 0. And then we take our parameter, which has components of minus 2, and 1. So here there's no restriction on our vector components, and the parameter t is any real number. So for each vector b, the linear system has infinitely many solutions. Suppose we have a matrix A which has p rows and q columns. There are 6 vector spaces for this matrix and its transpose. So for matrix A, we have the row space, the column space, and the null space. And similarly for the transpose of A, we have a row space, a column space, and a null space. Now given the row space of A is the same as the column space of its transpose, and similarly the column space of A is the same as the row space of its transpose, we have 4 distinct vector spaces, being the row space of A, the column space of A, and a null space of A, and a null space of its transpose. So these four distinct vector spaces are called the fundamental spaces of the matrix A. And therefore the rank of A is equal to the rank of its transpose, and therefore this implies that the rank of the transpose of A plus the nullity of the transpose is equal to P, where P is the number of rows in matrix A. So let's verify this for the transpose. So if we augment this matrix with the 0 vector and subtract 2 by row 1 from row 3 and 2 by row 2 from row 3, we get zeros in the final row. And therefore we can say that x2 is 0 and x1 is 0. So therefore the null space has a dimension of 0, and we can say that the rank of the transpose is 2. So therefore that's equal to P being the number of rows in A. Suppose we have a matrix A with P rows and Q columns, and suppose we have a subspace of RQ. So for example, that would be the row space of A and a null space of A, because the row vectors have Q components. Then the set of all vectors in the vector space of Q tuples that are orthogonal to every vector in S is the orthogonal complement of S, which is denoted S with a perpendicular superscript. So for example, if we have A with the following entries and we augment it with the 0 vector, then subtracting 2 by row 1 from row 2, we get 0 and minus 3. And then multiplying the second row by minus a third, we get a 1. So this matrix is now in row echelon form. So therefore the solution tuple is x1, x2, x3. So in this case x3 is 0, and x1 minus 2x3 is 0, so that means x1 is also 0, and x2 can take on any value to satisfy those two equations. So x2 is a real number in the open interval from minus infinity to infinity. And here we have these two vectors spanning the row space of A. So these have components x equals 1, y equals 0, and z equals 2. So that's the first row vector. And the second row vector has components x equals 0, y equals 0, and z equals 1. So it looks something like this. So the span of these two vectors is the xz plane passing through the origin. So any vector in the plane of these vectors can be represented as a linear combination of these row vectors. So as we can see, the null space of A is the line along the y-axis, which is orthogonal to this plane. So therefore the null space of A is the orthogonal complement of the row space of A. And note that this plane extends to infinity in all directions. Recall that a function is a rule that associates with each element from a set X only one element in the set Y. So this rule is denoted Y equals f of x. So we can view it as a mapping from a set X to a set Y. So for example, if we have some element in set X, that gets mapped to an element Y1. So note that, for example, if we had a parabola, two different values of x can map to the same y value. So effectively it's a many-to-one mapping. So y is the image of x under f, or f of x is the value of f at x. And x is the domain of f, and y is the codomain of f. So for example, if we had a set X having elements 1, 2 and 3, and set Y has elements 1 to 4, and our rule f of x is equal to x squared. So in this case, the domain of f is the set with elements 1, 2 and 3, and the codomain of f is the set with elements 1 to 4. And the range is the subset of the codomain that consists of all images of points in the domain. So effectively the range is the actual values that these x values are mapped to according to the rule that's given. So in this case, the range of f is the set with elements 1 and 4. So the square of 1 is 1, the square of 2 is 4, and the square of 3 is 9, which is not inside this set. Now we'll extend functions to vector spaces. So if we have vector spaces v and y, and f is a function with a domain v and codomain of y, then f is a transformation from v to y, or f maps v to y. And if the two vector spaces are identical, then f is also an operator on the vector space v. So if we consider some real valued functions of q variables, so we have some function of x1 to xq, which maps this tuple to y1, And similarly, we have y2 is another function of x1 to xq. And so on, up to yp, which is some function of x1 to xq. So here we have p equations that assign a unique point or vector having components y1 to yp, which is in a vector space of p tuples, and this unique point or vector gets assigned to each point or vector being x1 to xq that's in the space of q tuples. So we denote this as a transformation from the vector space of q tuples to the vector space of p tuples. So we're going from x to y. And alternatively, we can write this transformation as y1 to yp being equal to t of x1 to xq. Now recall our transformation from the vector space of q tuples to the vector space of p tuples. And now if we have a special case where the equations are linear, so we have y1 is some coefficient of a matrix by x1 plus a12 by x2 and so on up to a1q by xq, and we have a similar expression for y2 being equal to a21 by x1 plus a22 by x2 and so on up to a2q by xq, and we keep going up to p equations. So we have ap1 by x1 plus ap2 by x2 and so on up to apq by xq. So this can be written as the vector y is equal to the matrix A being the matrix of coefficients multiplied by the vector x. So effectively, A is a transformation that maps a column vector in the vector space of q tuples to a column vector y in the space of p tuples. So we can denote this transformation as TA from the vector space of q tuples to the vector space of p tuples. And again, if we have the same number of independent variables as dependent variables, so where p is equal to q, so in addition to being called a transformation from rq to rp, it's also called the operator. So this transformation can also be expressed as a vector resulting from the transformation of the vector x. Or another notation states that TA maps x to y. So A is called the standard matrix for this transformation. Let's look at several properties of matrix transformations. So for every matrix A, the matrix transformation from the vector space of Q tuples to the vector space of P tuples, where A is the standard matrix for the transformation, then this transformation has several properties for all vectors A and B in the vector space of Q tuples, which we're transforming from, and also for every scalar S. So the first property is the transformation on the zero vector results in a zero vector. So you can look at this transformation as a matrix A multiplied by the zero vector. And we also have two additional properties stating that the transformation is linear. So the first property of linearity is the transformation of the scalar S multiplied by a vector A is the same as the scalar multiplied by the transformation of the vector. And the transformation of a sum of two vectors is equal to the sum of their individual transformations. So the transformation of A plus the transformation of B. So using these linearity properties of a matrix transformation, we see that a matrix transformation maps linear combinations of vectors in RQ. So if we express a vector as some linear combination of other vectors up to R, so this here is a linear combination of a vector in RQ. So transforming this linear combination by the linearity property results in the following linear combination of these vectors. So we have the scalar S1 by the transformation of vector A1 plus S2 by the transformation of vector 2, and so on up to SR by TA of AR. So linear combinations of vectors in RQ get mapped into corresponding linear combinations in RP. And another property that results from linearity is if the transformation from RQ to RP and another transformation with another standard matrix B from RQ to RP, and if the transformation TA of a vector x is equal to TB of the vector x for every vector x in Q space, then the standard matrix for this transformation is equal to the standard matrix for this transformation. Let's look at our method for finding standard matrices for the transformation from Q space to P space. So this transformation, for example, can be a rotation, reflection, orthogonal projection, and so on. So to find a standard matrix for a transformation, we first consider the effect of the transformation on the standard basis vectors of RQ. So for example, if we have the transformation of the basis vector E1, that's equal to the transformation matrix multiplied by the basis vector. And similarly, we have a transformation of vector E2 being equal to A by E2, and so on up to the transformation of a vector EQ being equal to A by EQ. So as we know, the standard basis vector E1 has the first component being 1 and the remaining components being all zeros. And E2 has all zeros except for the second component. And so on up to EQ, which has the Q component being non-zero. So remember that we can express the multiplication of a matrix by a vector as a linear combination of the matrix columns with the vector components being the coefficients of the linear combination. So for example, the matrix A by E1 is equal to 1 by column 1 of matrix A plus 0 by column 2, and so on, plus 0 by the final column of the matrix. So as we can see, this is the same as column 1. And if you do the same thing for the matrix A by E2, well, you're going to get a 1 multiplied by column 2. And so on up to the matrix by EQ, which will be equal to the column Q in matrix A. So therefore the transformation matrix A is obtained by augmenting the transformations of the standard basis vectors in each column. So what we have is the transformation of the basis vector E1 augmented with the transformation of E2, and so on, which is finally augmented with the transformation of the standard basis vector EQ. And keeping this transformation matrix in mind, we're going to go through several examples where we develop standard matrices for a linear transformation. Let's develop a standard matrix for the orthogonal projection of some vector with components x and y onto the horizontal axes. And recall our standard matrix for the transformation can be written as the transformation of the basis vectors in each column of the matrix. See, here we have 2 dimensions, so we'll stop here. So first, our projection operator applied to the vector with components x and y should result in a vector with components x and 0. And now we'll find the images of the standard basis vectors. So the transformation of the standard basis vector E1 we expect to remain as 1, 0. So remember that E1 is a unit vector with components 1, 0. And the standard basis vector E2 is a basis vector with components 0, 1. So therefore the orthogonal projection of E2 onto the horizontal axes is going to give a point, or a vector with 0 length. So therefore the standard matrix for this transformation is obtained by placing the transformations of each standard basis vector in each column of the transformation matrix. So for the first basis vector we have 1, 0 and 0, 0 for the second basis vector. So therefore, if we apply this transformation matrix to any vector with components x and y, we get 1 by x is x plus 0 by y, and the second component is 0 by x plus 0 by y, which gives us the expected result. Let's derive the operator to do a reflection about the xy plane. So suppose we have a vector with some x coordinate, y coordinate, and z coordinate. So it looks something like this. And to reflect that about the xy plane, we expect the vector to look something like this. So the x and y coordinates remain the same, but the z coordinate gets negated. So therefore the transformation operator on a tuple xyz results in the following tuple. And now we'll apply the transformation to each standard basis vector. So we have E1 which has components 1, 0, 0. So reflecting this vector about the xy plane results in the same vector. And for our next basis vector, being the unit vector E2, which has components of 0, 1, 0, well, this vector is also going to remain the same if we reflect it about the xy plane. And finally, we apply the transformation to the third basis vector, which points in a z direction. So it has components 0, 0, 1. So the image of this vector, if we reflect it about the xy plane, is going to be 0, 0, minus 1. And now we place these images of the basis vectors in each column of our reflection operator about the xz plane. So what we have is 1, 0, 0, 0, 1, 0, and 0, 0, minus 1. And this is our standard matrix for the reflection about the xy plane. So in general, if you multiply this by some vector x, y, z, we have x by 1 plus 0 by y plus 0 by z, and then 0 by x plus 1 by y plus 0 by z, then 0 by x plus 0 by y plus negative 1 by z, which is our reflected vector as expected. Suppose we want to rotate a point or vector through some angle theta about the axis pointing out of the plane. So again, we look at what the transformation is going to do to our standard basis vectors, being E1 and E2. So E1 would be rotated by the angle theta, and similarly for E2. So these vectors will be rotated anti-clockwise by some angle theta. So applying our transformation to E1, which had initial components of 1, 0, well, the transformed vector is going to have a horizontal component of cosine theta and a vertical component of sine theta. So note that these basis vectors are unit vectors. So when we rotate them, they still have a length of 1. And applying the transformation to the second unit vector, our second unit vector had initial components of 0, 1. So its new components are minus sine theta, which is this component over here, and the vertical component is cosine theta. So these are the images of the standard basis vectors. So therefore our standard matrix is cosine theta, sine theta in the first column, and minus sine theta, cosine theta in the second column, which is our standard matrix for a counterclockwise rotation through the angle theta. Now let's multiply this standard matrix by some vector with x and y components. So we'll take the image of this vector as having components xt and yt. So if we multiply this matrix by this vector, we get x cosine theta minus y sine theta and x sine theta plus y cosine theta. So these are called the rotation equations for R2. So these equations are for a counterclockwise rotation. But if we wanted to rotate a vector clockwise by the same angle, then you just replace theta with minus theta. Let's derive the standard matrix for shear in the x direction. So if we have our standard basis vectors, and visualize these as forming a square, well, a shear transformation in the x direction is going to distort this square so it becomes a parallelogram. So our vector e2 ends up here, and the basis vector e1 remains unaffected. So applying the transformation on each basis vector, we have the transformation applied on e1, which results in an image of 1, 0. So this vector remains unaffected. And then applying the transformation on e2, which has initial components of 0, 1, well, the component of this vector in the horizontal direction is our shear factor, and the vertical component remains the same. So therefore our standard matrix for this transformation is 1, 0 and S1. So note that if S is less than 1, then our shear distortion will be in the opposite direction. A composition of matrix transformations is when we combine transformations to perform an overall transformation. So if we have a transformation A from Q space to R space, so for example, we have our vector space RQ, and we do a transformation A on some vector in RQ to get to R space. So this here will be TA of V. And we do another transformation B to go from R space to P space. So that would look something like this. So we end up with our image of the transformation A of V. So we have TB of TA of V. So the transformation from RQ to RP is denoted with the circle operator. So essentially, we're applying TA on V first, and then we're applying the transformation TB. And this is the same as this composition, which is also the same as applying the transformation matrix A to the vector V, and then applying the transformation matrix B. So we have the composition of transformation B with transformation A applied to the vector V. Now in general, compositions are not commutative, so the composition of transformation B with transformation A is not the same as the composition of transformation A with B. And this can be seen, for example, if we reflect a vector about the line y equals x. So suppose we have a vector with x and y components. So the reflection across this line would look something like this. So let's suppose this is the reflection transformation applied to V, and then we project this reflected vector onto the x-axis. So we have the composition of an orthogonal projection and a reflection. But what if we did this the other way around? So suppose we first do the projection of V onto the horizontal axis, So this is our vector, which will start like this. And then we do the reflection about the line y equals x. So therefore this vector will now be reflected as follows. So this yellow vector was the result of our first composition, and this is our result from the second composition, which you can see are different geometrically, and I'll leave it for you to actually multiply these two transformation matrices in both cases, and you'll see that the compositions are not commutative. But note that some cases are commutative, such as the composition of a reflection about the x and y axes. A matrix transformation from Q space to P space is 1-to-1 if the transformation maps distinct vectors or points in RQ to distinct vectors or points in RP. So effectively, given the same transformation applied on vector v1, we get the image of vector v1, and applying the same transformation to v2 gives a completely different vector in P space. So for example, the rotation operator on R2 is 1-to-1. So for example, if I have a vector v1, if we apply the transformation matrix to this vector to rotate at 90 degrees anti-clockwise, the image of the vector is as follows. And suppose we had another vector v2 and we rotated this anti-clockwise by 90 degrees. So v2 gets mapped to its image. So as we can see, we have distinct vectors resulting from the same transformation on R2. Now orthogonal projections are not 1-to-1. So for example, if we had some vector v1 and another vector v2, so these have the same x coordinate but a different y coordinate, then the projection of these vectors onto the horizontal axes is the same. So therefore the projection transformation is not 1-to-1. If we have a 1-to-1 matrix operator, so it's a mapping from Q space to the same space, and it's a 1-to-1 mapping. So note that the transformation matrix will be a square matrix. So 1-to-1 means the transformation matrix is invertible. So effectively the inverse operator is denoted as follows. So it's a mapping from RQ to RQ. So effectively, if we apply the transformation A on a vector and then apply the inverse transformation, then that's the same thing as A by its inverse multiplied by the vector, which gives the identity matrix multiplied by V, So effectively, applying the inverse to the transformation reverses the transformation and returns a vector. So for example, if we have the rotation matrix being a square matrix which rotates a vector anti-clockwise in 2 space. So we've previously derived this. The inverse of this matrix is equal to 1 over the determinant, which is 1 over cosine squared theta minus sine squared theta. So by the trig identity, this will give 1. And then we swap A and D. So cosine theta gets swapped with the other one. And negate B and C. So we get sine theta minus sine theta. So if you multiply these together and apply your trig identities, then you're going to get the identity matrix. Now suppose we have the projection transformation. So the matrix for projecting a vector onto the horizontal axes we derived previously as 1, 0, 0, 0 in 2 space. And in this case, you can see that the determinant of this matrix is equal to 0. So the inverse does not exist. And as we saw previously, the projection transformation is not 1-to-1. So a projection of different vectors can result in the same projected vector. Let's determine if this is a matrix transformation from 3 space to 2 space. So for this to be true, the transformation must satisfy the linearity properties. So if we apply the transformation to the sum of 2 vectors, v1 and v2, then that should be the same as applying the transformation to each vector and summing the images together. And the other property is the transformation on a scalar multiplied by a vector is the same as multiplying the scalar by the image of the vector. So considering 2 vectors with components x1, y1 and z1, and x2, y2, z2, then the transformation of v1 plus v2 in component form is the transformation applied to the following tuple with components x1 plus x2, y1 plus y2, and z1 plus z2. So on the right hand side, we end up with 4 by x1 plus x2 plus y1 plus y2 and the second component of the image is minus 3 by x1 plus x2 plus z1 plus z2. So as we can see, if we transform vector 1, which is the following tuple, we obtain the image as 4x1 plus y1, and the other component is minus 3x1 plus z1. And similarly, transforming the second vector with the following components gives 4x2 plus y2 and minus 3x2 plus z2. And if you add these components together, you get the exact same components. So adding these two components gives this component. So the first linearity property is satisfied. And now checking the second property, if we transform a scalar by each component of vector 1, so we have the following tuple. So that's going to give 4 by the scalar by x1 plus the scalar by y1. So that's the first component of the image. And the second component is minus 3 by the scalar by x1 plus the scalar by z1. And you can see that multiplying this transformation by s on both sides and factoring out s from this vector gives the exact same result. So therefore this is a matrix transformation.